Okay. Good evening. Good evening. Can you hear me? Good evening. Can you hear me? Yeah. Fine. Let's get started. And from my first class, the main idea in analyzing analog circuits was the first step, probably in design in analyzing analog circuits, is modeling, right? So we have done device modeling because I told you this is not a device course; it's a design course. So we need a specific equivalent model for all these devices, so that when you connect them, right? When you connect them, you will be more comfortable in analyzing them, right? A simple model. And first, I've taken a bulb. A bulb is very complicated inside. It's got a filament, everything. But when you draw the characteristics of the bulb, you realize that the bulb is a resistor, is it not? So what is the resistor behavior for DC and AC devices and their equivalent models? So first we have taken a resistor, and with the help of a resistor, we have done the voltage division rule and the current division rule, right? And we have done KVL and KCL, and we realize that if you have a resistance of some value, right, R ohms like that, the value is going to be same whether it is DC or AC. So resistor behavior is not going to change because V equal to Ri and dV by di is also R. So the value of R does not change if it's V by I or dV by di. But because R equal to V by I and R is same as dV by di, right? So probably resistance is the only parameter which does not change its behavior for DC and AC. Then slowly we have introduced the capacitors and inductors in my introduction course, right? Capacitor for DC, it will fully charge. When it gets fully charged, it does not take any current. So no current means open circuit. So you have maximum voltage across the capacitor, and the capacitor model, equivalent model, is an open switch for DC. And capacitor allows AC, so we have replaced capacitor with short. Inductor gives a completely complementary picture. It is short, low impedance for DC and high impedance for AC. And with these two simple models, our main aim is not modeling, our main aim is to go a step further, right? So what is the step further? We started analyzing simple filters. We said that if with the help of these switches, I will know whether a filter is a low pass filter or a high pass filter or a band pass or band stop, right? So we have done all sorts of filters using these models. And then we introduced diode also. The diode for DC is going to give you 0.7 volts, 0.7 volts drop. So with this 0.7, wherever you find the diode, take 0.7, and if the current is positive, the diode is forward bias. With this, we have done clippers, clampers, peak detectors, voltage multipliers, just by replacing diode with 0.7 and calculating the current. But what happens if you apply a small signal? If you apply a small signal, then the diode is replaced by a resistor. A resistor RD, whose value is VT by capital ID. And this capital ID you can find from DC analysis. You can find from DC analysis. So with this simple resistor, we have replaced a diode with the resistor, and we have done something called the small signal analysis of a diode, right? But only with 0.7 volts DC, we have done a lot of things. We have done clippers, clampers, peak detectors, multipliers, right? Fine. Then we introduced BJT. But because BJT has 3 terminals, or rather 2 ports, right? There's an input port and an output port. At least 2 elements are needed to know its DC and AC behavior, right? DC behavior we have done in biasing. In biasing, I said that a diode also has a BJT also has a diode here. So we have to take 0.7 volts between base and emitter. So wherever base and emitter is there, if you forward bias, you can take 0.7. So you can take 0.7 here, right? And then what is your IC? Your IC, if you connect an emitter resistor, we have seen that this IC is beta by beta plus 1 times of IE. But if you don't have an emitter resistor, then you might use this IC equal to beta IB, right? IC equal to beta IB. So IC is beta by beta plus 1 times of IE, and or IC is beta IB. And wherever you find a diode between base and emitter, you can take 0.7. So with this, what we have done? With this, we have done all sorts of DC analysis, right? We have found the region of operation. If you want to find the region of operation, whether the BJT is in cutoff or active or saturation, this is the model we have used, right? And we have done the different biasing circuits where the BJT, you have taken 0.7. And then we wanted to apply a small signal. And I told you, if you apply a small signal, the diode is no longer 0.7 volts. The diode has to be replaced by a resistor, right? So we had a resistor here. This R pi. And here, GM V pi or VB. If this voltage is V pi or VB. So this is the AC behavior of a BJT. And if you have early effect, then you can also include something called R0. Am I right? R0. You can take GM V pi, or you can as well have beta IB also. Right? If there is an IB here. It's one and the same. So this is the AC model of the BJT. On this, what we have done? With AC model, we have done CB, CE, CC, and differential amplifiers, all sorts of amplifiers on by replacing BJT by the AC model. And of course, what is R pi? R pi is going to be beta by GM. And what is GM? It is going to be IC by VT. And what is R0? R0 is going to be early voltage by ICDC. Early voltage by ICDC, right? And by knowing these values from the DC analysis, then you can replace the BJT with the AC equivalent, and then you can. So that means the diode behavior and the BJT behavior is no different. The diode for DC is 0.7. The transistor also for DC at the input side is 0.7. And the diode for the AC is a resistor. The BJT for the AC between the base and emitter is a resistor. And what about the output? The output side is same. IC is beta IB or beta IB. It's one and the same. So IC is always beta IB if it is DC or AC. There's no difference between the diode analysis and the BJT analysis. 0.7 volts for DC. So you have to tell this in your mind, right? 10 times in your mind. 0.7 is for DC, resistor is for AC. 0.7 is for DC, resistor is for AC, right? 10 times you have to tell this, or at least tell this in your mind. 0.7 is not there for AC. 0.7 is not, should not be considered for AC. Resistor should be considered for AC. I'm doing AC analysis, differential amplifier, I should not consider 0.7. 0.7 is only to calculate the DC current. At least this you have to tell in your mind, right? 0.7 should not be considered for AC analysis. 0.7 should not be considered for AC analysis. 0.7 should be considered only for DC analysis. For AC analysis, you have to put a dynamic resistance R5 there, right? And what about MOSFET? MOSFET, we have found MOSFET to be much simpler than the BJT. The gate, source and drain. The gate current IG is 0, right? Whenever the current is 0, you can replace MOSFET by the open circuit. Here, it's an open circuit. And what is ID? This ID for a MOSFET is K times of VGS minus VT whole square by 2. And what is the value K? It is mu C ox W by L. So if you take this, and if you find that your VDS is greater than VGS minus VT, then your MOSFET is fit to be an amplifier, right? Otherwise, it might go into triode region, right? So this is the model we have used for MOSFET in DC. And then last class, we have introduced small signal analysis. The current is 0. If you differentiate also, it's going to be 0, however. So it's VGS here, GM VGS or V pi, because there's V pi there. Input V pi here, right? It's GM V pi, and then an R naught. So there is no difference between the BJT analysis and MOSFET analysis. But what is GM? GM is going to be, right, DID by dVGS. It is going to be mu C ox W by L into VGS minus VT. And if he gives early effects, your R naught is early voltage by ID. So with this AC analysis, we have done common source, common drain, common gate, and all those, what you call, common source, common gate, common drain, right? And the differential amplifiers and all that we have done, right? And finally, op-amp, right? There's no special model for op-amp. Op-amp is basically a VCVS, a voltage control voltage source. So you can use a VCVS model for op-amp. So op-amp is this, plus minus V0 and VD. All right, so you can have VD here. So this is V1, V2. You have Rn or RID. This is R0. This is A times of VD. So this is the model we have used for op-amp. Okay. Did everybody settle down? Yeah. Good evening, good evening, good evening. Good evening. Is my voice audible?
Yes, sir, audible.
Yeah. Okay, so this is the model we have used for op-amp. This is the model we have used for what? Op-amp. And V1 and V2 are the inputs, and V0 is going to be A times of V, right? A times of V. Okay. Now, if you want to solve some old gate problems, maybe 10, 15 years back problems, then this comparison might be handy for you. Similarity between pi model and H model. Similarity between pi model and H model. So have R pi here, beta IB, R naught. And in H model, if you solve old gate problems, then the gate examiner, here you'll have HI, there's HFEIB, there's 1 by HI. So this model you can use for AC analysis, right? But the examiner doesn't know which model you're using. The final answer, you can make a comparison. For example, your HI is directly, what is HI here? By comparing these two, you know that HI is R pi. And your HFE is nothing but beta. And your 1 by HOE is nothing but R naught, right? And what is R pi? R pi is going to be beta by GM, all right? And what is GM? GM is beta by GM is GM, all right? GM is always beta by GM is GM. So beta is HFE and beta by GM is HI. So your GM is going to be HFE by HI. If you want to make a comparison between the pi model, both are same, right? You can use this model, and because finally, if you need numerical values, then whether you call it HI or R pi, answer is beta by GM. You have to, your calculator should do, beta by GM, right? But in old gate problems, if you see, they used to give HI, HFE values, still easier. We are getting these values from where DC analysis, but in old gate papers, the examiner himself will give R pi and beta and R naught, which is HI, HFE and 1 by HOE. So directly you can, go for AC analysis. Without DC analysis, you can do AC analysis, right? So just for comparison, that means what is the model we've been using till now? It is H model only. I didn't mention it is H. It's almost like the H model's old name, the transistor's old name, AC name is H model. New name for it is pi model, but it's the same transistor. Model is for the same transistor, so your answer is not going to change. Whether you do by H model or pi model, your answer is not going to change, right? So many models are there. Pi model is more popular. Even T model, some books, they even do this T model. This is also popular. So in T model, you have base here, emitter, collector. So this is your VB here, but the current here is IE. Then what should be this resistance value? This resistance for T model, you can call it RE. You can call it emitter resistance RE. So if you see through the emitter resistor, what is the value of RE? RE is going to be VB by IE. It is VB by IE. But what is IE? What is IE? What is IE? IE is nothing but, or what is the relationship between IE and IC? Alpha equal to IC by IE. Am I right? So what is IE? It is IC by alpha. So it is alpha by IC by VB. It is alpha by GM. So we know in a BJT, the resistance seen through emitter, terminal is nothing but alpha by GM. Am I right? Okay, so this is alpha by Gm. And here you can have a Gm V pi or VB or beta IB. This is collector. And where will you connect R naught? Where will you connect R naught? This is base emitter collector. Base emitter collector. Where will you connect R naught? R naught is connected between collector terminal and emitter terminal. Between collector terminal and emitter terminal. So between collector terminal and emitter terminal, you have to connect R naught. So this model is called the T model. It's called what model? T model. You can use this model also and do it. Your answer is not going to change because there if you use pi model, every current will be in terms of IB. IB, numerator IB, denominator IB, numerator IB, denominator IB. If you do by T model, your numerator IE, denominator IE, numerator IE, denominator IE, when you're doing voltage gain. But our model is still different, right? We are directly writing numerator IC, denominator IC by dividing emitter resistors by alpha and base resistors by beta. And wherever VB is there, we will write 1 by Gm instead of R pi or alpha by Gm, right? So our model is still, I don't know what we should call that model, right? We're doing it mentally. Wherever we find an emitter resistor, we divide by alpha, base resistances by beta, right? And wherever VB is there, this across VB, we don't write R pi or we don't write alpha by Gm, we write 1 by Gm, 1 by Gm, because 1 by Gm is a value for MOSFET also. So it's much easier for us to do the comparison between the BJT analysis and MOSFET analysis. Okay, right? So it's your wish. If you want to solve some old gate problems, HI is there. Wherever HI is there, just convert it into R pi and do it. Wherever HF is there, convert it into beta and do it. 1 by HOE, you make it R naught and then try to solve. Your answer is not going to change. Okay. Okay, so yesterday we have done the differential amplifier, and the differential amplifier, the main reason people went for differential amplifier is they hated capacitors, right? They hated capacitors. Capacitors cannot be fabricated on IC. So we have to be shy of using capacitors on an IC. Suppose if you connect some capacitors and give it to the fab unit, the fab fellow will make you a call and say that, is there a way to remove these capacitors because I can't fabricate them, right? So maximum you should see that you don't use capacitors. Here and there, one capacitor in the order of picofarad is allowed, and that is for the dominant pole compensation. If you want some stability in an op-amp, it's accepted somewhere here and there you can have one capacitor, but 1 microfarad capacitor at coupling capacitor, 47 microfarad, 470 ohms RE. See, that is a typical value in discrete components when you do this experiment in the lab, right? Common emitter amplifier, 1 microfarad at input, output 0.1 microfarad, and RE across RE or C is 47 microfarad. Such big value of components, if you give them to a fab unit and say that common emitter bring it on IC, then he will say it's not possible. Are you getting? Right? So never use capacitors in any of your design, right? All the design that you had with capacitors are outdated. You have to find a way to eliminate the need for capacitors. And how did we eliminate them? The need for the coupling capacitor, we eliminated if you bias the BJT with a negative supply. Bypass capacitor is no longer needed if you can somehow bring a 0 volt at the emitter. How can you bring a 0 volt at the emitter? If you connect two transistors and you give a common signal to them, then the emitter node is going to experience a virtual ground. So this is something called the phase splitting. The same signal is cut into two parts, right? V in by 2 for first BJT and minus V in by 2 for the second BJT. And why do we call it as a differential amplifier? Because when you see the Q1, Q2 transistors and the resistors here, whatever happens at the left side, if you see the right side, it is going to be 180 degrees phase shift. If you measure a voltage VC1 with VC2, 180 degrees phase shift. VE1 with VE2, 180 degrees phase shift. Anything that you do left side, the right side, if you see, it's always going to be 180 degrees. So that is called the differential. That's called differential. So that is why the amplifier is also called a differential amplifier, right? And there are so many ways of solving it. One popular way I told you, right? So you can directly take a collector current in one loop and collector current in the other loop. And wherever VB comes, you just write 1 by Gm, 1 by J. That is one method. And still lazy method is if there is a symmetry. If there is a symmetry, then the gain of half circuit is equal to the gain of full circuit. The gain of half circuit is equal to the gain of full circuit, right? Okay. So we'll have one or two now. Find V naught by V, beta large. Vt is 25 millivolt. Find V naught by V, beta large. Vt is 25 millivolt. Now, how will you solve circuits if a resistor is connected between base and collector, right? If a resistor is connected between base and collector, then how do you solve? You can solve by Miller's or you can directly solve by small signal. So I will solve such circuits also. If you have an ungrounded capacitor or ungrounded resistor between the base and collector, then we know a theorem called Miller. So we will do that also later, right? So how do you design this current source? Let me design a simple current source. What value should I take here? Minus 3.3. Now see here, these type of questions, when students go for jobs, right, VLSI jobs, in the field of analog or whatever it is, right? So the students keep telling that these type of questions they give, when you go for TI interview, the written test and all that. So this is very popular. It's called the uh, MOS. It's called the MOS telescopic cascode. So the cascode, double cascode, the telescopic cascode. So these type of structures they give, and they ask you to find the gain just by inspection, right? But if you do by the conventional textbook way, right, small signal model, and replace all the MOSFETs with small signal, so it's difficult. Just by looking at the structure, you should be able to assess the gain of the amplifier, right? M1. So you can see that the M5, M6, M7, M8, they are acting like resistors, right? They are load, active load. Upper PMOS is going to be acting like resistors, active load, and the lower one is the cascode amplifier. Okay, so we will solve it. You will understand. Problem 1. Okay, so let's get started. So how do you solve this, right? Before going for AC analysis, first we have to look at DC analysis. DC analysis. Now, the good thing about why is differential amplifier easy than the voltage divider bias? The simple reason is below the emitter, just below, can you see the emitter terminal here? Below the emitter, whatever you draw, that is for biasing, that is for DC. Just above the emitter, whatever you draw, Q1, Q2 transistors, they are for AC analysis. So lower portion is for DC, upper portion is for AC. But in BJT, voltage divider bias, circuit looks simple, but the big headache. Resistors will be in series for DC. They will come in parallel for AC. So complete stunt will be there. But if you look at the simple differential amplifier, this is a virtual ground. This point P is at virtual ground for AC analysis. You're least bothered what happens down. So the lower portion is for DC analysis. So in DC analysis, self-bias, what did we do? You tell me. IC/DC equal to VCC R2 by R1 plus R2 minus VBE by RE plus R1 parallel R2 by beta plus 1. That is the voltage divider bias DC analysis. What is DC analysis here? See here. This is DC analysis. This is DC analysis. That's all. Your DC analysis is over, right? What you have to do? You have to write current source. This is DC, I0. What is your IC/DC? Your IC/DC, each transistor is going to have a current that is half I0 by 2, which is going to be 1 milliampere. So that ends your DC analysis. But in self-bias circuit, what did we do? we took two transistors, R1, R2, RC, then we applied Kirchhoff's law, Thevenin, KVL, right? No nonsense is here. Simply, the moment you find a current, the tail current, this is called the tail, right? So differential amplifiers, tail current is the DC analysis current. So that's it. Once you finish DC, what is GM? GM is IC by VT. It is 1 milliampere by 25 millivolt. It is 1 by 25. So this completes your DC analysis. Now we go for AC analysis. For AC analysis, instead of analyzing the whole circuit, we have to take only half of it, right? Because the gain of half is equal to the gain of full. Gain of half circuit is equal to the gain of full circuit. The gain of half circuit is equal to the gain of full. So we'll draw only half. So this is the popular common emitter amplifier. Your V0 and this is V. For AC analysis, voltage sources should be short. So what is V0 by V? V0 by V, which is the differential gain, is going to be minus of something by something, right? It is minus 3K by 1 by GM. It is minus GM into 3K. Minus GMRC. This is very popular, right? Common emitter amplifier. Gain is minus GMRC. Minus 1 by 25 into 3000. So 25 ones are 25 and 5 remains, 25 twos are 50, right? So it's minus 120, I think. Is it correct? Minus 120. Okay. So I told you the tail portion is for DC analysis, upper portion is for AC analysis, this point P. This is ground for what analysis? AC analysis. So you don't need to connect a capacitor from P to that, minus 10 volts. There's no point because this is 0 and minus 10 is also at 0. So it doesn't need a bypass capacitor. So the lower portion is for DC, upper portion is for AC analysis. So let's see what is the DC current I0, DC analysis. DC analysis. So let me draw the transistor here. And please don't forget the basic theory that I told you. VE, IE, IC, VC. VE, IE, IC, VC. So this is your IC, I0. So what is our first step? First step is VE. So if you come down, you have to subtract. So it is I've given minus 3.3, minus 3.3, oh my God, minus 3.3, minus 0.7. So if my mental mathematics is correct, I wanted a round figure there. So I wanted here to be minus 4, right? then what is my current I naught here? I naught is going to be minus 4 minus of minus 10 by 2K. So it is 10 minus 4, that is 6 by 2K. So this is going to be 3 milliampere. It is going to be how much? 3 milliampere. Then what is your ICDC? ICDC is I naught by 2, which is 1.5 milliampere. 1.5 milliampere. So I repeat, VE, IE, ICVC. So first VE is minus 3.3 minus 0.7. It is minus 4. Minus 4 minus of minus 10 by 2K. 1.5 milliampere is ICDC. Now, we have to go for AC analysis. AC analysis. In AC analysis, the gain of full circuit is equal to the gain of half circuit. So this amplifier, just now we have done. So what is V naught by V? The differential gain. This is the differential gain, AD. So it is generally V naught by VD. VD means the signal that is applied between the two terminals. This VD is nothing but V in. V in. And V naught, what is V naught here? VC1 minus VC2, right? It's VC1 minus VC2. Or you can, if somebody gives V in 1, V in 2, then it is V in 1 minus V in 2 also, right? Whatever it is, VC1 minus VC2 by V in, which is V naught. What is this gain? Minus GM into RC. What is GM? It is ICDC by VT, 25 millivolt, into RC is 5K. So that therefore, the differential gain AD is 25, 5, 15, 5, is it 300? Is it 300? Please let me know. Is it 300? 15, 5, 75, 25 goes 3 times. Is it minus 300? Yeah, it's minus 300. Yeah, thank you. So the differential gain is minus 300. See, such problems are even asked in IES exam for 12 marks, 15 marks like that, right? So by the moment you find a problem, you'll think that, oh, there are 3 transistors in it. So maybe 3 transistors means a bigger problem. No, this is much simpler than the voltage divider bias. In voltage divider bias, the divider is not stiff. There's a Thevenin equivalent there, KVL and all that stuff, right? But here, it's much, in fact, if you can do it orally also, right? Some students will just do it orally, right? They will think that I naught is minus 3.3, minus 0.7, minus 4, minus of minus 10 by 2K. That's 3 milliampere. So there should be 1.5 there. So what is GM? 1.5 by 25 millivolt into 5K. So that's, I can't do 1.5 by 25 into 5K or in my mind, but some students, they are very good at math. They'll, in their mind, they calculate it like, minus 300, right? Okay. Okay, so similarly, what should I do to this REE? When this end goes up and this end comes down, differential, then the middle point is going to be at what ground? Virtual ground. So this REE, we are going to split it into 2 resistors. Do you remember? We have done this, right? So let me draw half circuit for this. REE by 2. So your V in is going to be V in 1 minus V into half circuit. And your V naught is going to be VC1 minus VC2. The gain of half circuit is equal to the gain of full, right? But what about Q3? Whenever you find a diode, you can write it 1 by GM3 parallel with R pi. Please, this is 1 by GM parallel with R naught if it is a MOSFET. This is a BJT, so I'm putting 1 by GM parallel with R pi, right? So these two are in series. These two are in series. So how will you write V naught by V? V naught by V. So let me put it like this. So this is going to be RC plus 1 by GM3 parallel with R pi. Why did I put a plus sign there? Because the two components here, this resistor and this both are in series, right? This is RE by 2. So what is V naught by V? Your V naught by V is going to be minus of something by something, all right? So what are you going to write in the numerator? Imagine the collector current here and collector current here. This is IC and this also IC. Of course, this is already IC. So directly you can write RC plus 1 by GM3 parallel with R pi. Now, what is VB in terms of IC? VB in terms of IC is 1 by GM. 1 by GM. And what is, here there is no IC, there is IE, actually it is IE. But if you imagine it is IC, then you have to write RE by 2 by alpha. RE by 2 by alpha, right? So if the examiner gives the current I here, then it's the same I flowing as collector because two sources are there. Then what is GM? GM is going to be IC DC by VT. So you can substitute there, right? So this is the gain of the amplifier for 4 transistor circuit, right? So 1, 2, 3, 4, 4 transistor circuit, no small signal model. Intuitively, we have solved this. Now, in both the previous problems, we had passive resistors, right? So you have passive resistors, so you can always neglect what? Passive resistors, you can always neglect R0, right? R0, and you can, in the question, at least you can mention VA is infinite. VA is infinite. Even if it is not infinite also, the value is going to be small because passive are there. VA is infinite, all right? Okay. But what about this? What about this here? This is fine. If the examiner gives the early voltage is infinite, you can do it. Otherwise, the small value is there. Can you see a small value RC plus? This is a passive element. This should come in parallel with this value R0 plus. That's a very big number. R0 plus 1 plus GM R0 into that, right? It's not needed. So in this problem also, I'll mention VA as what? Infinite. If you want, you can take that value. That a large resistance parallel with a small resistance, it is always going to be small value. It's always going to be small. Okay, so this is, I think, this is an IES problem for 12 marks, I think, but you can do it directly. Tell me. Now, first DC analysis. For DC analysis, DC current is already there. I naught 2 milliampere. Then what is IC? It is I naught by 2. It is 1 milliampere. And what is GM? IC by VT. 1 by 25. So this completes the DC analysis, right? So what is the AC equivalent? For AC equivalent, we can replace current sources with open circuit and voltage sources, DC voltage sources with short circuit for AC analysis, right? So let us draw like this. Now, yesterday I told you a trick. You can imagine collector current here, and you can imagine collector current here, right? If you imagine collector current, then what is VC2 by V? Your VC2 by V is going to be, the current is going to ground, it is positive, right? So what will you write here? 5K by, in the denominator, there are two transistors, 1 by GM plus 475 ohms by alpha plus 475 ohms by alpha plus 1 by GM. Now, if beta is larger, beta is infinite means alpha is 1. Alpha is 1. Beta is infinite. Alpha is 1. Right? And what is 1 by GM? It is 25 ohms. 1 by GM is 25 ohms. So what is 25 plus 25? Or what is 25 plus 475? 25 plus 475 is 500. And this is 25 plus 475 is 500. So it is 5K by 25 plus 475 plus 475 plus 25. So 500 plus 500 is 1000. So what is VC2 by V? Your VC2 by V is going to be 5000 by 1000. It is 5. The gain is going to be 5. Now, why did we get less gain here? Less gain, naturally, because there is an emitter resistor. We all know that emitter resistors will have an extra factor along with 1 by GM. So emitter resistors reduce gain. Emitter resistors will always reduce gain. Input resistance, they will improve because R pi plus 1 plus beta times of Re. So input resistance will improve, but the gain, whenever you find an emitter resistor, naturally the gain is going to reduce. So your VC2 by V finally is going to be how much? 5, right? And please, left side if you take minus GMRC by 2, right side if you take plus GMRC by 2, like that also you can do, right? You can take a half circuit, and half circuit means what? Minus GMRC. Left side it is minus GMRC by 2. Right side it is plus GMRC by 2. When you take half circuit, what are the terms that are missing in the denominator? If you take half circuit, what are the terms? A 475 and a 25 will be missing. Only 475, 25 will be there. But that is for the differential output in the middle here, right? But if you take left side, it is going to be minus GMRC by 2. Right side, it is going to be plus GMRC by 2. So whatever the gain that you get by removing two terms in the denominator will be in the middle. Half of that value will be left side, other half is going to be right side, right? So again, you have to divide by 2. Instead of putting these 475 2 times, you will take half circuit. Final answer, what you have to do? Because right side it is half. Again, you have to divide by 2. Instead of dividing by 2, same term you can put 2 times in the denominator. The answer is same. Is it not? Your answer is same. This is simple mathematics. What mathematics will tell you here? I'm not that good at math, but I know in mathematics that if you have something like this, yeah. See here, if you have something like this, x by y plus y, am I right? X by y plus y. This is nothing but, this is one way of doing it, right? So it's going to give you x by 2y, x by 2. What is the other way? You take half circuit x by y, and then final answer, you're going to do x by y by 2, am I right? By 2, because right side is going to be half. So your wish, Either you want to put y 2 times and get x by y by 2, or take half circuit. So if you take half circuit, this is what you get, right? Final answer is x by y by 2. If you directly do it, you're going to get x by y by 2. Are you getting, right? Okay. Fine. So this is an IES problem. So obviously IES problem for 15 marks, those problems will never have what effect? Early effect, right? Early effect. Early effect problems are only when transistors are connected with what? Transistors. And the upper transistor has R0 and the lower one has R0. Then we cannot neglect R0. If you have passive elements, 1K, 2K, 3K means finished. There is no early effect. Even if you take early effect, what you will get? Instead of 5, you will get 4.999 you will get. Are you getting? This is waste of time doing with early effect. Right? That is why examiner, most of the problems, there is no early effect at all. But off late, what is happening is, he's changing the paper from passive loads to active. When he's going towards active, you have, instead of 5K, if you have another transistor, instead of 475, you have another like this problem, right? Everywhere there is MOSFET, right? So the upper ones are resistors now. M7, M5, M8, M6 are resistors, load resistors for that. And the lower one is the, a cascode MOSFET, right? So it's called telescopic because it's kind of long, right? So it's called telescopic cascode. So how do you solve this telescopic cascode, right? The gain of full circuit is equal to the gain of half, right? So we will draw half circuit first. Half circuit. We bias points, we can ground it. Now, how can we do this in a simple step? For doing this, first you should know how to solve a common source amplifier. If you know how to solve a common source amplifier of one transistor, then you know how to solve for all these 4 transistors. So a common source amplifier says that if you have a single transistor where you apply Vin, and this is V0, this is suppose RD, then what is V0 by Vin? V0 by Vin is minus of something by something. What is something? Input side, it is 1 by GM1 because the transistor is there. Output side, you have to put the output resistance. What is output resistance? It is RD parallel with R0. It is RD parallel with R0. This is R0. Are you getting? So it is this the lower resistance parallel with the upper resistance. The lower resistance parallel with the upper resistance. If you know this, then the same thing is here. What is V0 by Vin here? It is the output resistance divided by where the loop is. The loop at the input says that it is 1 by GM1. But the output side here, output resistance says that there is some resistance here, Rx, and there is some resistance here, Ry. The upper portion is Ry, the lower portion is Rx. So you can have Rx parallel with Ry. You can have Rx parallel with Ry by 1 by GM1, right? This is just a load. Instead of 2 transistors, you can imagine one RD. In the place of RD, who is there? In the place of RD, there is what you call, there is M5 and M7. In the place of R0, you have Rx now. You have Rx. And of course, in this loop, you have 1 by GM1 at the input. Now, what is Rx and what is Ry? What is Rx and what is Ry? What is Rx and what is Ry? Shall we do this here? Where Rx equal to, tell me, what is Rx here? There are 2 resistors here, R02 plus 1 plus GM2 R02 into R01 into R01. This is approximately GM2 R02 R01. This is Rx. What is Ry here? Ry equal to R05 plus 1 plus GM5 R05 into R07. This is approximately GM5 R05 R07. Right? So this is the Rx and Ry. We got this value. So the answer is V0 by Vn. Final answer is minus GM1 into Rx parallel with Ry. GM2 R02 R01 parallel with GM5 R05 R07. So this is the answer for 8 transistors, right? 8 MOSFETs. 8 MOSFETs, right? So this is minus GM into RD parallel with R0. This is, of course, this is only for your understanding. This is only for your understanding, right? So this is how you have to solve this. So this is given for students while they go for the VLSI, test in Texas Instruments, I think. So some students, they send how to do it. Fine. So VC2 is a voltage across this 5K. So we have to take 5K here by this. Are you getting? So it is only, and what is VC1? Tell me. What is VC1 by Vn? VC1 by Vn is same as VC2 by Vn with a negative sign. With what sign? Negative sign. And what is V0 in the middle? What is V0 in the middle? If you take V0 in the middle is going to be VC1 minus VC2. V0 in the middle is going to be VC1 minus VC2. Is it not? So that you can get V0 you can get by taking half circuit, right? VC2 right side is this value. VC1 left side is the same value with a negative sign. And what is V0? V0 is going to be VC1 minus VC2, right? That V0 you can get by taking half circuit and do it, right? Your wish. You can take half and do it, but that will be V0. Right side will be half. Left side is also going to be another half with phase shift, right? See, to understand this problem, you should know that if denominator increases, the value will decrease. Who is more? V0 is more or VC2 is more? Always V0 is more. VC1, VC2 are less. So to get less value, the denominator should be increased. So you should know that simple logic, right? In mathematics, whenever you have a P by Q form, right? If denominator keeps on increasing with so many terms, then naturally the value is going to decrease. Too many terms in the denominator, value is decreasing. Less terms in the denominator, value will increase. So who is a big value, V0 or VC2? V0 is big, so denominator should be less. So half circuit you have to draw. Half if you draw, less value in the denominator, you get more. The gain of half and the gain of full are same. But if you want left side, right side, then you can extend the denominator, or whatever you get V0, you divide by 2, right? Please don't forget, left side in the differential amplifier is minus GMRC by 2. Right side in the denominator, right side is plus GMRC by 2. In between is going to be minus GMRC by 2, minus of plus GMRC by 2, it's minus GMRC, right? So don't forget, if denominator increases, the value is going to decrease. The value is going to decrease. Oh, instead of M2, I have put M2 here, but this is M3, no? This is M3. I put M2 here. So what can we do? Should we change the whole thing? No, I will put M2 here, right? Shall I put M2? This is M2. Call this M3. That is better. Okay. So now it's fine. The question I've changed. This is M2, but out of hastiness, I put M1, M2 here. But this M2 in the main question? No, it's M3. Good catch. Some student said, okay, very good. Okay, so this is about the differential amplifier. The gain of half circuit is equal to the gain of full circuit if there is symmetry, right? Okay. Now, how do we solve multi-stage amplifiers? A simple logic. Multi-stage amplifiers. Multi-stage amplifier. Now, when you do multi-stage amplifier intuitively, when you're directly writing the answer, there is a possibility that a student can make a small mistake. That small mistake, if you understand, then even for 10-stage amplifier, 20-stage amplifier also, you can directly write the answer, right? So what is a simple mistake a student can make? Let us take two common emitter amplifiers. Cascaded. They are cascaded. And you want to find V0 by V. V0 by V. So if you want to find V0 by V, then the first impression what a student gets is each common emitter amplifier is going to give a gain of minus GMRC. So when you cascade two stages, the first amplifier will give minus GMRC, second amplifier will give minus GMRC into minus GMRC will be the gain, right? So that is a mistake. Why it is a mistake, right? Q1, Q2 transistor, you are right. Q2, the last transistor, you are always right. But intermediate stages, there is something called loading effect. There's something called loading. So what is that loading is? Let me do it. A simple motivation for that is, okay, yeah. Now, can you say that if you have a, fine, we'll draw the small signal model. Otherwise, one problem we will do. First problem I will always solve by small signal. And then we will understand what is the mistake we are doing. And then we can motivate ourselves. And then we can go for multiple stages. Any stage, 10 stage, 20 stage is not a problem, right? Okay. So first draw AC equivalent for this. For AC equivalent, you have R pi, GM V pi or V pi 1. This is the first transistor. Here you have second transistor. R pi, GM V pi. So two transistors are there. Let us make the connections. Both emitters are grounded. Both emitters are grounded. Okay. Then base terminal. From base to ground, we can give V. This is base. This is collector. From collector to ground, there is RC. And collector is also shorted here to base. Collector is base. And then the collector to ground, you have a RC here. Here you get V naught. V naught. And this node is Vx. This is V. Now, if this is GMV pi, what is the current in opposite here? V naught is minus GMV pi 2 into RC. Into RC. Now here you have V pi 2. Now you can apply current division, right? Or if this is GMV pi 2, what is this current? Minus GMV pi 2. So V pi 2 is equal to the total current multiplied by the total resistance also you can do, right? What is the total current? It is minus GMV pi. We can combine both the resistors as RC parallel with R pi. This is our V pi 1, right? This is V pi 1. Now what is V pi 1? V pi 1 is same as V. V pi 1 is same as V. Now tell me, what is V naught by V? V naught by V can be written as V naught by V pi 2 into V pi 2 by V pi 1 into V pi 1 by V. Am I right? So what is V naught by V pi 2? Very good. Minus GMRC, no problem. Minus GMRC for Q2 transistor, no problem. Q1 transistor, V pi 2 by V pi 1, there is minus GM into RC parallel with R pi. There is something called loading here. For the first stage amplifier, the input resistance of Q2 has also come into picture. The input resistance of Q2 has come into picture, minus GM into RC parallel with R pi. What is V pi 2 by V? It is 1. It is 1. So the first stage is going to give the second stage is going to give minus GMRC. The first stage is going to give minus GM into RC parallel with R pi. So what is this R pi? Why R pi has come? Why R pi has come here? Why R pi? Now, first I will motivate you with this diagram. See here. Suppose I am having RC here. RC. And I want to find V naught by V. V naught by V. What is V naught by V? It is minus GM into RC. If I put an RL here, do you think this, you will not consider this RL? No. RC and RL are going to come in parallel. So V naught by Vin is going to be minus GM into RC parallel RL. RC parallel RL. Are you getting? Now you can remove RL. You can remove RL and you can connect a BJT here like this. So who is in the place of RL? Who is acting as a load here? The load resistance here is going to be the input resistance of this stage. So who is RL here? This RL is nothing but the R pi. You see through base resistance. Okay. Fine. If you are not happy with this explanation, we'll go for the block. Suppose you have two amplifiers. Amplifier 1 cascaded to amplifier 2. Amplifier 2. Now, for amplifier 2, we don't have a problem. But for amplifier 1, you should never forget that the input resistance of the second stage is going to act like a load resistance for the first stage. The input resistance of the second stage is going to act like a load resistance of the first stage. So whatever the value is there, RC, you have to take parallel to R in 2. R in 2. Are you getting? Consider the input resistance of amplifier 2 will act as load for amplifier 1. The input resistance of amplifier 2 will act as load for amplifier 1. So if you don't consider this, so amplifier 1 thinks that now previously I had RC, now I'm having RC parallel with RL. Won't you consider RL? When you consider RL, you have to consider the BJT also, right, from here to ground. Now, all of you, with this motivation, tell me, same problem if I give you like this, what will you write? Next time, somebody gives you a problem like this, how are you going to do it? V naught, this is RC, RC1, RC2, V. This node you can call it Vx. All right. So tell me, what is V naught by Vn? It is simply V naught by Vx into Vx by V. Am I right? So what is V naught by Vx? Last stage is not a problem. V naught by Vx is common emitter. It is minus Gm into Gm2 into Rc2. What about the first stage? It is minus Gm1 into Rc1 parallel with Rc1 parallel with R pi 2. That's right. Rc1 parallel with R pi 2. That extra R pi 2 you have to consider. Are you getting? So if you understand this logic, when you practice more, then if you understand the extra input resistance, input resistance, input resistance, you have to consider while keeping on writing for multiple stages. Now, all of you, just tell me, if I have a three-stage, any number of stages, it's one and the same. Then how will you solve a three-stage common emitter amplifier? Tell me, V naught by Vn is going to be V naught by Vx into Vx by Vy into Vy by V. Am I right? So last stage is never a problem. So what is the gain of last stage common emitter? Minus Gm3 into Rc3. This is not a problem. Am I right? But when you're writing for second stage, what you have to do? It is minus Gm2 into Rc2. But for the second stage, who is also the load? Who is also the load? The input resistance of third stage is going to be the load. And what is the name of this terminal? Base. So we all know that if the load is connected to base terminal, if that node is connected to base terminal, that means there is a load resistance of R pi. But instead of base, if you connect it to emitter, when will you connect to emitter? Suppose Q3 is not a common emitter amplifier, it is a common base amplifier. It's a common base, you connect it to emitter, you have to simply write alpha by Gm. If you connect anything to collector, then it is R0, right? Okay. So tell me, what is minus Gm2 into Rc2 parallel with R pi 3? Am I right? And what about the third stage? Tell me, first stage, it is minus Gm1 into Rc1 parallel with, Rc1 is going to be parallel with whom? R pi 2. That's right. It is going to be parallel with R pi 2. So like this, multiple stages you can write. Are you getting? And of course, if there is early effect, what is there? This resistor Rc3 will be parallel with R0, right? That's not a big thing. One more extra R0 we will put, right? Now, what is the input resistance of MOSFET? MOSFET, it is infinite, so there is no need of RPi. There is no RPi in MOSFET. RPi is infinite. So in MOSFET amplifier, you get minus GMRC multiplied by minus GMRC multiplied by minus GMRC. So MOSFET is such a good device where if suppose this is RD1 connected to another MOSFET, what is the input resistance here? It is infinite. So your RPi is not there, it is infinite. So directly you can write the answer now. So there is no loading in MOSFET, right? There is no need for you to consider the load of the next stage for MOSFET. So you have Vx here, Vy here. What is the input resistance here? Your Rin is going to be infinite, right? So MOSFET is excellent now. So if you want to do V0 by V, it is going to be V0 by Vx into Vx by V into Vy by V, Vx by Vy into Vy by V, right? So what is this? These are 3C amplifiers, C with C with C. 3-stage amplifier. This is CS, common source with common source with common source. All right. So if there are 3 common source stages, then V0 by Vx is going to be minus GM3, M1, M2, M, minus GM3 into RD3 minus GMRD. What is Vy by Vx by Vy? It is again minus GM2 into RD2. What is Vy by V? Minus GM1 into RD1. So is it not a clean circuit, right? There is no question of loading here because the gate terminal does not draw current. What is the current drawn by gate here? Ig is going to be 0. When it is 0, the resistance is infinite. This is an open circuit. So when you draw the small signal model, it will be very nice, right? Open circuit, current source, then open circuit, current source, then open circuit, current. So you can individually do it as if Q2 does not see Q3 and M2 does not see M3 and M1 does not see, M2. They are like perfect isolated, right? Even if M1 peeps like that and see that he just sees an open circuit there. And M2 is peeping like this, it's just an open circuit, right? So minus GMRC into minus GMRC into minus GMRC for 3-stage common source amplifiers, for 3-stage common source amplifiers. So for these problems, I have considered VA as what? VA as infinite. Otherwise, you have to include an extra R0. You have to include an extra R0. What if we cascade common emitter with common base? Now, this is called cascode, but the benefit of cascode we will see later, right? Right now, we are just calculating the gain. We don't even know it is cascode. We only know there is some stage called common emitter and it is given to common base, right? A common emitter with common base. So how do you draw common emitter? This is RC, all right? Okay, let me name this. Input is given at base, output is taken at collector, emitter is grounded. That is called common emitter. Common base, input at emitter, output at collector, base is grounded. That is called common base. Input at emitter. So collector should be shorted to which terminal? collector should be shorted to emitter, base is grounded. This is C, right? A slight change we have to make in Cascode. We will do that later. Right now, you think that it is cascading. Cascade. What do you mean by cascading? When the output of one is connected to input of the other, it is called cascading. What is cascading? What is cascading? When the output of amplifier 1 is connected to input of amplifier 2. When the output of one amplifier is connected to input of the other, then it is called cascading. Am I right? So now we can have a Vx here. Vx. What is V0 by Vin? V0 by Vin. How will you do it? Right? V0 by Vin can be written as V0 by Vx into Vx by Vin. V0 by Vx into Vx by Vin. What is V0 by Vx? Common base amplifier. You can draw separately like this. You remember, okay, guys, what is there? RC2, Vx. Vx we can draw like Vx. All right. Now you can imagine single current. You can imagine single current. Numerator what you'll write, denominator what you'll write. If you imagine a current here, RC2. It is 1 by GM2. So common base amplifier gain and common emitter amplifier gain both are same. Both are same. I already told you, but except for the 180 degrees phase shift. So this is also GM into RC. This is also GM into RC. Now what about Vx by V? Vx by V. For Vx by V in what you have to do, you have to take the common emitter and RC1 is there. Now the input resistance should also you have to draw. But what is the name of this terminal? The name of the terminal is E. E means emitter. E stands for emitter. How do you know it is emitter? There is an arrow here. There is an arrow. Whenever you see the arrow, then you know it is emitter, right? Emitter. Whenever there is an emitter, current is bada current, chota resistance. What is the resistance through emitter? It is alpha by Gm. It is going to be alpha by Gm. Are you getting? Alpha by Gm. So this alpha by Gm and RC, they are going to come in parallel. They are going to come in parallel. So what is Vx by Vin? It is again the common emitter amplifier gain minus of RC1 parallel with alpha by Gm2 by 1 by Gm1, right? Or we will write Gm2 RC2, which is the second amplifier, into minus Gm1 into RC. You can see, if you remember formula for common emitter minus Gm RC, you can directly write, yes or no? Minus Gm RC1 is in parallel with the input resistance, which is alpha by Gm2. Alpha by Gm2, you have to write. Are you getting? This is V0 by Vn of two-stage amplifier. It is two-stage amplifier. So if you want to check, please draw the small signal model and check, right? And draw the small signal model and check. So it is Gm2 RC2 into minus Gm2 Gm1 into RC1 parallel with alpha by Gm2. Why did I write alpha by Gm2 instead of R pi? In the previous case, this was the base terminal, right? Base means R pi, emitter means alpha by Gm. So this is cascading, common emitter with common base. What is analogous to this value? Analogous to this. Tell me what is analogous to this. Common emitter is nothing but common source. Common base is nothing but common gate. Common source with common gate. So just the symbol is there, no? The symbol, transistor symbol is there. For this transistor symbol, one extra line if you draw here, one extra line, and these lines you make straight, then it will become MOSFET. So if you want to draw MOSFET, then just remove the transistor, put another device like this. That is enough, right? Rest else is same. One extra line here you have to draw, and these two lines straight if you draw, becomes a MOSFET. So this is common source. This has to be given to common gate. In a common gate, gate is grounded. Common source, common gate, some node Vx, all right? Tell me, what is V naught by Vn? V naught by Vn is V naught by Vx into Vx by Vn. All right. What is V naught by Vx? This is common gate. Common gate amplifier gain and common common gate amplifier gain and common source amplifier gain are same except for the negative sign, right? So this is going to be GM2 into RD2. GM2 into RD2. So you never have a problem for the first, M2. You only have a problem with M1. In M1, the input resistance of this stage should come in parallel with the RD1, should come in parallel. You can see here, I have written here, this RL, can you see? RL here is in parallel with RC, is in parallel. This is ground, so you can short it there. They are in parallel. So what will you write here? Vx by Vn is going to be minus GM1 into RD1 parallel with, this is a source terminal, it will give you 1 by GM. 1 by GM2. So V0 by Vn is going to be GM2 RD2 into minus GM1 RD1 parallel with 1 by GM1. What is alpha? What is alpha for MOSFET? MOSFET, it is 1. Alpha for MOSFET is 1. So now we know how to cascade common emitter with common emitter with common emitter with common emitter, or common emitter with common base. We know how to cascade, right? Or common source with common gate. We know how to do it, right? Any other combinations we know, right? What are the ways of cascading? How many ways you can cascade? You have 3 configurations: CE, CB, CC, or CS, CG, CD. How many ways you can combine them? What does your mathematics say? How many ways you can combine? So common emitter with common emitter, common emitter with common base, common emitter with common collector. Similarly, common base with common base, like that. So 9 combinations you can have. Yes or no? When you are combining 2 to 9 combinations. Out of 9, we will try only 5. The other 4 you should never try, right? Don't try it at home. Don't try, right? Buffer with buffer, you should never try. For example, common base with common base. You should not try, right? If you connect common base with common base and connect microphone and say hello, hello, hello means complete only heat will be generated. No voice will be there. Only heat, right? For winter season, it will be good. Only heat will be coming from BJT. So buffer with losses should not be there. When you're combining, what is our main aim? Our main aim is that the overall performance of amplifier should not degrade. It should improve. So what combinations can we expect? The combinations are, of course, you want more power gain. C with C is one good combination. Cascode, right? Wonderful amplifier. For all the amplifiers, Cascode is number one. We will spend some time on that, right, today. So CE with CB. And CC with CE is also a wideband amplifier. CC with CE. Now we are going to see CC with CE. And of course, common collector with common collector, like a composite pair. You can have a Darlington pair. That combination is also widely used. So CE with CE, Cascode, CE with CB, and CC with CC, that is the Darlington pair. And what? You can even combine three, right? Common collector at the input stage and common base at the output. Yeah, so common collector with common base. That is also a wideband amplifier. Common collector with common base. That means a combination of a voltage buffer with a current buffer, right? So CC with C. So 5 combinations we will see. These are the only popular combination in textbooks, right? Don't draw your own circuits. Students, they will draw their own circuit and say, sir, what will happen here, right? Don't draw. First, what our great grandfathers have told, you have to first learn them, right? 5 combinations are there in the book. These 5 you will try, and these 5 I will teach also, right? Okay. Now, what happens if we take a common collector and give it to common emitter? Common collector with common emitter. CC with CE. Common collector input is given at base, output at emitter. Collector is connected to ground or supply. Common emitter, input at base, output at collector. Emitter is grounded. So try to draw this circuit. Try drawing this. How will you draw? Input is given at base, output is taken at emitter. This from emitter, we have to short it to the base terminal. To the base terminal. Sorry, this is CC. So similarly, you know what is your next circuit? The next circuit is going to be a MOSFET version of this. So CC is nothing but common drain with common source. Common drain with common source. Okay. So Q2 is not a problem. We know it. We'll take this Vx. V naught by Vin is V naught by Vx into Vx by Vin. So what is the gain of C amplifier? Minus GMRC. This is not the problem. But CC amplifier, the input resistance, what is the name of this terminal? Let me draw this. The name of this terminal is base. So from this node to ground, you have to connect R phi 2. Am I right? So now tell me, what is this? This is RE parallel with R phi by RE, or if you want me to divide by alpha, after dividing by alpha, what will you get? RE parallel with R phi by RE1 parallel with R phi 2 plus alpha by GM. You get, right? Or if you want, you can divide this by alpha, this by alpha, and this by 1 by GM, right? So it is RE parallel with alpha, okay, whatever it is. This is a gain. All the emitter resistors are divided by alpha, base resistors are divided by beta. Is it not? Emitter resistors are divided by alpha. This is Vx by V. Or you can do RE parallel with RE1 parallel with R pi 2 divided by, that is the emitter current. And what is the base current here? The base current, you can multiply the numerator with 1 plus beta, and at the denominator, if you imagine base current, you can write R pi plus 1 plus beta times of this value. Or if you imagine emitter current, then this is going to be what value? It is minus GM2 into RC2. If you imagine emitter current, then this alpha in the denominator will go RE1 parallel with R pi 2 by RE1 parallel with R pi 2 plus alpha by GM. V naught by V. And remember, collector is connected to supply. What is supply? Ground for ACNR. Please, what is this terminal? What is this terminal? Can you see here? What is this? So just repeat in your mind, right? 10 times you have to repeat. VCC is ground for AC analysis. VCC is ground for AC analysis. 10 times you have to repeat in your mind. VCC is ground for AC analysis. VCC is ground. Collector is connected to ground. Are you getting? Common collector. So what is V naught by V? It is V naught by Vx into Vx by V. See, this is a beautiful amplifier. What is the input resistance of M2? Here, infinite. Infinite, is it not? So individually you can solve. What is V naught by Vx? Minus GM2 RD2. And what is Vx by Vin? Imagine a single, there is no imagination. There's only one current here. It is RS1 by RS1 plus Vin. It is 1 by GM. So this is a beautiful amplifier, is it not? The input resistance is infinite. It is RS1 by RS1 plus 1 by GM. So this is something like this. Yes or no? So Vx by Vin is going to be RS1. For Vx, what is Vx? ID into RS1. What is Vin? VGS plus ID into RS1. Vn equal to VGS plus ID into RS1. So RS1 plus 1 by GM. This is V naught by V. So now we are left with, apart from the Darlington pair, the last combination is nothing but a voltage buffer with a current buffer. It's a voltage buffer with a current buffer. You have to connect a voltage buffer with a current buffer. So who is a voltage buffer with a current buffer? Common collector with common base. Common collector with common base. Right? So how do you draw this common collector? Input is given at base, output at emitter. Common base, input at emitter, output at collector. See here, this is a very nice circuit. It looks like a differential amplifier because in all the differential amplifiers, we have seen that the emitters are connected, right? But a common collector with common base, emitters are connected. Can you see here? Emitter of first is connected to emitter of the second. So you can draw emitter of the first transistor to emitter of the second. In common collector, collector is grounded. That means collector should be connected to supply. In common base, output is taken at collector and base has to be grounded. Base has to be grounded. Input is given to base. This is input. Here we have to give input. Here we have to take output. Output, right? Here collector is grounded. Here base is grounded. Are you getting? So this is a CC amplifier. This is a CB amplifier. But if you think that, sir, what about biasing? Because biasing mostly we are neglecting for simplicity. If you want biasing, then you can have a tail current here. This is open circuit for AC analysis. Open circuit for AC analysis. So this is a CC with CB. This is what? A CC with CB. Right? And just now we have done. If you take right side, what will be the gain of a differential amplifier? Left side, if you take the gain is going to be minus GMRC by 2. Left side, right side, if you take plus GMRC by 2. So your V0 by Vin is going to be plus GMRC by 2. Plus GMRC by 2. Here, because the current shifts, both have the same GM. Both have the same GM. So, or if you don't like it, we can split it as Vx here. As Vx. So when you split it as Vx, then how will you solve it? So let's imagine both have the same transconductance. Otherwise, you can put GM1, GM2. What is there? Let us assume both have the same GM, and there is Vx here. So what is V0 by Vx? V0 by Vn is going to be V0 by Vx into Vx by V. So the last stage is never a problem. The last stage is never a problem. It is a common base stage. So common base will give you a gain of GMRC. Common base is going to give you a gain GMRC. But what is Vx by V? What is Vx by Vn? For knowing Vx by Vn, for Vx by Vn, what is the input resistance of this stage? That is going to be the load for this. So let me write it here. Common emitter, the load is going to be alpha by Gm. Alpha by Gm. This is output. Vx. So what is Vx by V? Emitter resistors have to be divided by alpha. Alpha by Gm by alpha by Gm by alpha plus 1 by Gm. So this is going to be 0.5. It's going to be 0.5. So what is V0 by V? It is V0 by Vx into Vx by V. It is going to be GMRC into 0.5. 0.5. Can I write 0.5 as 1 by 2? I can write, right? 0.5 can be written as 1 by 2. So GMRC by 2, we can write. So this is something we have solved there, Vx by Vn. We try to solve in the next page, right? So the input resistance of the common base amplifier is alpha by Gm. So we put there That is why, see, differential amplifier is probably the only topic where alpha beta will not be there, right? Ultimately, the MOSFET answers and the BJT answers are going to match, right? Okay, so we have 2 minutes now for 7 o'clock, and we'll take a break after that. So what is the last MOSFET combination of this we are left with? The MOSFET combination is common collector is common drain. Then see here, common collector with common base. So what is common base? Common base is common gate. And we know how that structure looks like. It looks like a differential amplifier. Okay, shall we follow a new method for this? What is the new method? We have done that problem, no? We have done that new problem, so we will follow that method, right? New method. It's not a new method, we already done this, right? So what is the AC equivalent for it? The AC equivalent is like this. Like this. So now we have to imagine same current. Here there is some drain current ID. Here also drain current ID. But what is VGS? VGS is nothing but ID into 1 by GM. VGS is nothing but ID into 1 by. So wherever VGS is there, you have to write 1 by GM. There is a VGS here, there is also a VGS here, right? So imagine a single current. Tell me what is V0 by V. Now V0 is ID into RD. V0 is what? ID into RD. What is Vin? Vin is ID into 1 by GM plus 1 by GM. So Vin is ID into VGS. VGS is 1 by GM plus 1 by GM. ID gets cancelled. GM RD by 2. So if you take right side, it is always going to be half GM RD by 2. Left side, if you take, suppose in this problem, there is no resistor. So drop is 0, right? The drop for AC analysis, this is ground, it will be 0. But what if I connect one more RD here, left side, one more RD? If I connect left side, one more RD, then left side you are going to get what? Because of RD, there will be some voltage drop. So it is going to be minus GMRD by 2. Left side is minus GMRD by 2. Right side is plus GMRD by 2. If you take in the middle difference, then it is going to be minus GMRD. And it is going to be minus GM into RD. Are you getting? And always remember, in the BJT problems, I told you, suppose there is a load. Load is 4.7K, right? I made it 1K, 2K, 3K, 4K, 5K like that. As long as the transistor is in active region, your IC is never going to depend on RC. That is BJT, right? Whether there is a symmetry in the circuit, no symmetry, that nonsense, that is different. If there is symmetry, we don't have to do 2 times. You are doing only once, right? If you want to calculate V0. But current distribution, you should not doubt. Why? Because if 2 transistors are same, first of all, even in a single transistor, your IC will never depend on RC. Your IC is going to depend only on the base voltage and emitter voltage. It is never going to depend on the collector. Whether there is a collector resistor or not, as long as current is flowing, the current will distribute, and that current IC is independent. Please remember, a BJT is in active region when IC is independent of VCE. IC is independent of VCE. IC is independent of VCE. VCE means RC. VCE means RC. IC is independent of RC, right? So even if there is no early effect, there is no early effect. Otherwise, one R0 we will put what is there, right? So your IC is going to get distributed into 2 parts. So never forget that, right? Because why I'm saying is, suppose in the same problem, if the examiner puts V naught here, what will you do? If the examiner puts V naught here, what will you do? Or V01, what will you do? V01 is same as V naught. V01 is same as V naught. What is V01? V01 equal to, this is suppose VA, this is VB. V01 is VA minus VB. VA is V naught, VB is ground for AC analysis. So if you take in the middle, if there is no resistor, then your V naught is going to be, V01 is going to be V naught. Are you getting? If there is a resistor, then left side is going to be half, right side is going to be half. When you take difference, it is going to get 2 times, right? Okay. Okay, we'll take a break now. When we come back, we will see more of other circuits. Okay. Can you hear me? Is my voice audible? Right. Now, in my first class, I mentioned that what are the things that you look in an amplifier? One is strength. The strength in an amplifier is governed by power gain, which is the product of voltage gain and current gain. Two is its impedance matching. Impedance matching. This is something to do with Rin and R naught. Rin and R naught. And third one is the frequency reach. This is something to do with tau and bandwidth. And we all know that bandwidth is simply 1 by tau. It is simply 1 by tau. Am I right? Fine. So we know how to calculate the voltage gain. We know how to calculate Rn and R naught. But what is the frequency reach of the amplifier? That means if I give a common emitter amplifier, a CA amplifier, now a CA amplifier is not going to give minus GMRC for all sine waves. For all sine, few sine waves are lucky, they get minus GMRC gain, but few sine waves, they don't get minus GMRC gain, especially the low frequency signals, they don't get minus GMRC. And the high frequency signals, frequency, what do you mean by frequency? Frequency means the number of waves per second is frequency. The high frequency signals, they don't get minus GMRC. And in the mid frequency range, you are going to get minus GMRC. So there is something called the cutoff, right? So there's something called a cutoff, a lower cutoff frequency and upper cutoff frequency. And the difference is the frequency reach. And the difference here is going to be the frequency reach of the amplifier. That is the difference between the omega H and omega L. But omega H for an amplifier, suppose omega H for a C amplifier is like, say 1 megahertz, 1 megaradians per second. And my lower cutoff frequency is 30 hertz. What is 1 megahertz minus 30 hertz? It's 1 mega. So upper cutoff frequency is very, very important. Of course, we'll calculate lower cutoff frequency because we have to solve, gate problems, IES problems. But bandwidth is decided by the upper cutoff frequency, not the lower cutoff frequency. So 1 megahertz minus whatever the value, small value, is always going to be 1 mega. So who is going to decide the bandwidth of an amplifier is only the upper cutoff frequency. So only few sine waves within that omega L and omega H value are going to have a minus GMRC gain. If there any sine wave that is going to have a frequency greater than omega H, finished, you don't get minus GMRC, right? So I'm going to draw a plot. I'm going to draw a plot now, and that plot will actually tell you the frequency reach of the amplifier. Only few frequencies are going to get minus GM into RC, not all the frequencies, only few between omega L and omega H, right? So if you give any sine wave that is slow moving, then you don't get minus GMRC. Any wave that's fast moving, you don't get minus GMRC. You get minus GMRC only for sine waves between omega L and omega H, right? Okay. So let's calculate that if the frequency reach of the amplifier. Calculate the lower cutoff frequency calculate the lower cutoff frequency, upper cutoff frequency, and bandwidth. Calculate the lower cutoff frequency, upper cutoff frequency, and bandwidth for the CE amplifier given. calculate the lower cutoff frequency, upper cutoff frequency, and bandwidth of the common emitter amplifier. Okay, so let me mention this. The frequency response of a common emitter amplifier is a band pass filter. Is a band pass filter. It is found that the coupling and bypass capacitors affect the low frequency gain. Whereas the parasitic capacitors or the junction capacitors, they are going to affect the high frequency gain. The coupling and bypass capacitors, they affect the low frequency gain, but the parasitic and the load capacitance, for example, this is driving another stage, and the input capacitance of the next stage also is going to come in parallel, and then the parasitic capacitors are going to affect the high frequency gain. Therefore, low and high frequency analysis are two independent problems. They are going to be two independent problems because the values of capacitors also, the coupling capacitors, they are in the microfarad range, and the junction capacitors of a transistor here, the junction capacitors, they are going to be in picofarad. So the low frequency analysis and high frequency analysis are totally two independent problems. They are two independent problems. One, the microfarad capacitor in series, they are going to affect the low frequency gain. The parasitic capacitors in shunt, the shunt capacitors, are going to affect the high frequency gain. Now, as a simple analogy, you can take this. Suppose I'm having a series capacitor and a shunt capacitor, right? So this network we have already seen in the introduction class, right? So why did I given in the introduction? Because a common emitter is going to behave like this. A common emitter is going to have a series capacitor and a shunt capacitor, right? CS and CP, or C1 and C2, series capacitor, shunt capacitor. Now, what is the frequency response of this? The frequency response is, for omega 0, for low frequency, capacitors are going to act like open circuits. They're going to act like open circuit. So if you open circuit here, your V0 is going to be 0. And at high frequency, omega infinite, capacitors are going to behave like short circuit. Now, what is the voltage across a short circuit here? Again, your V0 is 0. So in my first class, I told you if you have 0 here and 0 here, and it's a filter after all. It has to select some frequency. So maybe you'll get a response like this, right? Response like this. Okay, that is fine. Still, intuition is when will you get maximum gain? Tell me, when will you get maximum gain? Do you think when both capacitors are open, or both capacitors are short, or what combination can you expect? You get maximum gain when you can expect when C1 is a short and C2 is open. C2 is open. So however you try, you're not going to get any gain which is greater than R2 by R1 plus R2. So that's the maximum gain you're going to get here is by voltage division. So one is going to act like short, the other is going to act like an open circuit. So if you ask me, sir, why you didn't consider these capacitors till now for calculating the maximum gain minus GMRC, we made an assumption that all this C1, C2, C3 are short. C1, C2, C3 are short because this C1, C2, C3, this is okay, this C1 here, right? So these are the coupling and bypass capacitors, coupling and bypass capacitors. So if you consider them short for AC analysis, you get gain. But if you ask me, sir, you didn't consider these parallel capacitors here, C pi, C mu? Yes. When I didn't consider, that means they are open. I didn't consider them, it means they are open. So when it is open, the circuit will behave like this. So I shorted all the C1, C2, C3, which is the series capacitors here, C1, C2, C3, right? And now, the C pi, C mu, I didn't consider them, right? The shunt capacitors. So naturally, I was getting the maximum gain minus GM into RC, right? But at low frequency omega 0, the capacitor C1 is going to act like open circuit. Just tell me, when this acts like open circuit, C2 also acts like open circuit, but who is dangerous in these two? Why the signal is not, why your V0 is 0? Why V0 is 0? Why V0 is 0? Why V0 is 0? Is it because of C1 or is it because of C2? If C2 is open, there should be some voltage across the resistor. So C1 is responsible. The series capacitors are responsible, right? What about the parasitic capacitors now? Why V0 is 0 for omega infinite? Omega infinite, both are short. Both are short. Both are short. But then why V0 is 0? If this is short, signal should be transferred, but why? Why V0 is 0? C2 is responsible. So who is C2 here? It is the parallel. These are parasitic capacitors. Parasitic. These are the coupling capacitors. Coupling. Are you getting? The coupling capacitors are responsible for low frequencies, and the parasitic capacitors are responsible for high frequency. With a simple network, some idea we are getting. Are you getting? But we will calculate the cutoff frequencies. That is not a big thing. But without calculating also, by looking at the circuit, we can have some intuition as to what we have to do. Are you getting, right? Okay. So C1 is responsible for the coupling capacitors and C2 is responsible for the parasitic. Fine. C2 is the parasitic and C1 is the coupling capacitor. So what will be the frequency response of such an amplifier? So this is 3 dB down, 1 by root 2 times. So who is responsible here? The lower cutoff frequency is the coupling and bypass capacitors. This is the low frequency region, low frequency. This is something we call it as high frequency. And this is the mid frequency. So whatever the maximum gain, whether it's minus GMRC or whatever, when the gain falls down by 1 by root 2 times, that is where you take the cutoff frequencies, right? To get this, what is a simple technique? 1 by tau. If you do 1 by tau in the transfer function, then that's it, right? You're going to get the cutoff frequency. Calculate tau, right? So two ways are there. Either you make it 1 by root 2 in the transfer function, do all the mathematics, or multiply resistor with capacitor, right? So which is easy? I have resistor of 1 kilo ohm, capacitor of 1 microfarad, right? Resistor, capacitor. If you multiply 1 millisecond, 1 by 1 milli is 1 kilo over. What is the other way is you have to take the whole transfer function, right? The whole transfer function. You have to replace every capacitor here by 1 by SC, 1 by SC, 1 by SC. Draw the small signal model, take the transfer function and draw the Bode plot. And you have to draw the Bode plot, right? Very big transfer function you will get. Are you getting? So if you start morning, by evening, you will somehow draw the frequency response because 3 capacitors are there. And again, the small signal model, parasitic capacitors, 2 are there, 5 capacitors are there. At least by evening, if you start from morning, you can complete the Bode plot, right? Instead of calculating 1 by root 2, we will have a new method. What is the new method? We will have to calculate, just multiply resistor with capacitor, that's all. Take some R and C and then multiply. 1 by RC will be the cutoff frequency, right? So this is a technique used in books, right? Or because this is a Bode plot, the other method is you can take the transfer function and draw. That is also one method. Now, why is that when the gain is high, the coupling capacitors are short circuit and the parasitic capacitors are open circuit when the gain is high? When the gain is high, can you see here? When the gain is high, here, gain high. When the gain is high, why is that the coupling capacitors are short and the parasitic capacitors are open circuit? Let's see. Let us take some value, right? A simple value is coupling capacitors are microfarad. You can take 1 microfarad. Parasitic capacitors are picofarad, 1 picofarad you can take. What is micro? 10 power minus 6, pico is 10 power minus 12. So if you take omega of say 10 kiloradians per second, just some value, the mid frequency. Now, what is the impedance offered by capacitor? 1 by omega C. It is 1 by 10k, 10 power 4, C is 1 micro. It is 100 ohms, 100 ohms. So it is not short, it is offering 100 ohms in the mid frequency. Now, what is the impedance offered by a capacitor here? 1 by omega C. It is 1 by 10k, 10 power 4. C is 10 power minus 12. It is 10 power 8 ohms. So it is not an open circuit. It is not an open circuit, but it is 10 power 8 ohms. 10 power 8 ohms is very, very large. So you can treat this as open and you can treat this as short. It's not short, but you can treat it as short. So for all AC analysis, mid-frequency means what? This is our AC analysis. This is our AC analysis, which we've been doing. So whenever we are doing AC analysis, coupling capacitors are treated as short and parasitic capacitors, we didn't consider them. Not consider means they're very, very large. They are treated as open, right? Now, just tell me, if the denominator is 10K and you got 100 ohms and you got how much 100 ohms. What if the denominator increases? What if omega increases? Omega large. What happens if my omega is large? If omega is large, this value will be, if omega is large, this value is going to be less than 100 ohms, much, much less than 100 ohms. It is much, much less than 100 ohms because of omega large. So this is a perfect short here. So I'll be a fool if I consider coupling capacitors for high frequency, right? Or never consider coupling capacitor for high frequency because already it is a short for mid frequency. It is a super short for high frequency, right? Similarly, look at the denominator omega. For a certain omega, it is 10 power 8. For a certain omega, it is 10 power 8. What if omega is small? Omega is small. If omega is small, then this value, if the denominator is small, this value will be much, much greater than 10 power 8. Yes or no? It is going to be much, much greater than. So that means if this is open, it is super open circuit here. If this is an open, if you have not considered for mid frequency, you have no right to consider for high frequency when it comes to coupling and bypass. If you have not considered parasitic capacitors in our AC analysis, you have no right to consider it at low frequency because the value is still larger. Then with the process of elimination, we came to know that the gain is affected only by these two boxes. We have to consider this fellow. Consider. Why we have to consider? Because we are getting a plot like this, yes or no? The gain is affected. So the gain is affected by whom? You can't wait for this high frequency analysis. So low frequency, the gain is affected because of coupling capacitors. The gain is affected because of coupling capacitors. This is a point of intersection now for us. And the gain is affected at high frequency because of whom? The parasitic capacitors. So this is by the process of elimination. Because student will always debate. He'll say, why only this? Why not other? Why not other? Others, there is no scope. There is no scope in the other four boxes here. There is only scope here. Are you getting? So series capacitors are going to affect the low frequency gain. Parasitic capacitors are going to affect the high frequency gain. Because if your omega is small, this value will be larger than 100. It is going to be much, much larger than 100. And if you have a series capacitor, suppose there is R1 and this capacitor is much, many times larger than R1. If it is many times larger than R1, it is almost like an open circuit, then the signal is not going to the shunt arm. It is dropped in the series arm only, right? So this is our aim. We have to consider coupling and bypass capacitors for low frequency and parasitic capacitors for high frequency. We have to consider, right? Now again, there is another problem. But there are three capacitors. No? You have three series capacitors and you have two parallel capacitors. Dot like that. You are giving some input C1, C2, C3, C pi, C mu. So you have three series capacitors and three parallel capacitors. Then what you have to do? How are you going to calculate tau? Suppose you want to calculate for C1 alone, and how you are not going to stop the signal flow. The whole signal flow should be there. If you consider C1 alone for omega 1, then C2, C3 should be short. C pi, C mu should be open. Why we have to short? If you don't short, means signal will not be there, right? If you consider only due to C1, then you have to short these two and open. Suppose if you open C2, output, no output will be there. Your analysis is gone. Are you getting? If you want to know the effect of only C1, then other capacitors, you have to kill them. What is the best way to kill them? Series capacitor short, shunt capacitor open if you make, then you can find C1 alone. Then C2 alone. Then C3 alone. You have to do with the same procedure. So here you will get tau 1, here you will get tau 2, and here you will get tau 3. After getting tau 1, tau 2, tau 3, we will sketch. Next, C pi, C mu is there. If you consider C pi alone, then C1, C2, C3 are going to be short, or directly C pi, C mu you can combine. Shunt, no, two capacitors are in parallel, you can combine. But when you consider C pi and C mu, your C1 and C2, C3 all should be short. Are you getting? Right. So then you can have a plot like this, Here you are going to get three frequencies. Suppose this is C2, due to C2, due to C1 and due to C3 here. And here you have due to C pi and C mu, right? So this combination is going to give you omega L. This combination is going to give you omega H. And then we will have the best approximation. We will think of the best approximation. We will think of the best approximation. Are you getting? So this is a technique we are going to follow. Taking one, that means a most complicated circuit where we have to draw the Bode plot, almost the same answer we are going to, please don't underestimate this analysis. This analysis, the actual Bode plot, both are almost going to match, but that will take from morning to evening. This will, by seeing you can tell, right? But we will do step by step. Slowly you will understand that you don't have to do also, right? By seeing you can tell what is the bandwidth of the amplifier by inspection. Okay, so first we have to do low frequency analysis. Low frequency, taking one capacitor at a time. Oh, I can't keep searching all this. First we will draw AC equivalent. Tell me what is AC equivalent? I have a transistor here. There is a capacitor here, C2. RB, capacitor, resistor, RS, and here you have a RC, and RL. C3. Okay, this is the AC equivalent. Now, whenever we are calculating the equivalent resistance or equivalent capacitance, you have to short the voltage source. So now we will start the low frequency analysis. First with C1 alone. C1, this is also a gate question. Only C1 they have given. No C2, no C3. Examiner himself has not given C2, C3. Only C1 alone. C2 and C3 are replaced with short circuits. Then the examiner is asking, what is the tau value? So voltage source should be short, right? Now you tell me what is tau? What is tau as seen by whom? As seen by the capacitor. Please here, capacitor is seen. This capacitor is seen. Capacitor has two eyes, right? So capacitor is seen. Where is he seeing? Capacitor has how many terminals? Two terminals. So this is I, no? This is I. This I you have to remove from here and you have to connect here. This I also you have to plug and connect here. This is called seeing. It is called what? Seeing. The capacitor is seeing it there, right? And what is this? The name of this terminal? It is called base. What is the resistance seen through base? The resistance seen through base is the capacitor seeing here, R equivalent. Here we have RB. Here there is R pi. And here we have RS over, right? So tau is simply going to be, or tau 1 is going to be R equivalent into C1. It is going to be R equivalent into C1. What is R equivalent? Seen by the capacitor. These two are in parallel. The combination is in series. So it is Rs plus Rb parallel R pi into C1. Rs plus Rb parallel R pi into C1. Rb parallel R pi into C1. That is R equivalent as seen from here. As seen from here. Are you getting? So you have a, between the 2 points here, there is a resistor Rs. And from this point to here, you have another resistor Rb parallel with R1. So when you see here, these two you can combine, make them one. Then it is both are in series. So this is tau 1. So now what is the cutoff frequency due to this? If you know tau 1, then what is omega? Omega 1 is going to be 1 by tau. Omega 1 is 1 by tau. Omega 1 is going to be 1 by tau. Are you getting? Right? So from here, what is omega 1? Omega 1 is 1 by tau. Or if you want in hertz, it is 1 by 2 pi tau. It is 1 by 2 pi tau. It is 1 by 2 pi into Rs parallel, Rs plus Rb parallel with R pi into C1, right? So once you know tau, omega is not a big problem. Omega you can calculate. Omega is simply 1 by tau. Right? Omega is 1 by tau. So this is C1 alone. This is given for 2 marks, right? A simple transistor is given, only one capacitor. Examiner himself tells that neglect all other capacitances. See, examiner how nicely is framing a question. He's saying neglect all other capacitances. Only one capacitor he will give. With the help of that capacitor, you can calculate the cutoff frequency or time constant. The cutoff frequency or time constant you can calculate. Now, lower cutoff frequency due to C2 alone. See, now the nice space is there. C2 alone. C1, C3 are replaced with short circuits, right? So in this page, because of this AC equivalent, it looks a little clumsy. Now we can freely do it. Lower cutoff frequency due to C2 alone. C1, C3 are short. So now you have only C2. Here there is RC and here you have RL also. Only one capacitor we have to consider. This is RB and here RS. And your VS is 0. For calculating the Thevenin's resistance, VS should be 0, right? Now, what is R equivalent seen by the capacitor? Now the capacitor is seen, right? Capacitor is seen. What is R equivalent? Now the capacitor again, it has two eyes, right? Two eyes there. One eye you have to plug here, the other eye here, ground. So with respect to ground, what is the resistance? What is the resistance? Two plates are there. What is the resistance? And RS and RB, we can make them one. RS and RB, we can make them one. You can call it as RS parallel with RB. This is R equivalent. Now tell me, what is R equivalent, right? R equivalent is going to be, see, this single R equivalent, you see any textbook, for example, Cetera Smith or any book, 1.5 page they will do, because the R equivalent, for calculating R equivalent, they will replace the transistor by the small signal model, everything. But we already know it, right? If you see through emitter, it is already alpha by GM plus that resistor should be divided by how much? 1 plus beta. So if you know R equivalent, then there is no need for us. By inspection, we can say alpha by GM plus RS parallel RB divided by beta plus 1. And what is tau? Tau 2. It is R equivalent into C2. And what is omega 2? It is 1 by tau. 1 by tau. And what if you want in hertz, then it has to be 1 by 2 pi, right? If you want to in hertz. Radians per second, it is fine, right? F2, 1 by 2 pi tau, right? And what is the value of R equivalent? R equivalent is alpha by Gm plus this value. Are you getting? So F2 is 1 by 2 pi tau. What is tau? Alpha by Gm plus Rs parallel Rb divided by 1 plus beta into C2. Like, are you getting? Right? 1 by 2 pi tau. So this is lower cutoff frequency due to C2 alone. Due to C2 alone. Due to C1 alone, this gate problem, R pi and Rb are in parallel. The combination is in series with Rs. The combination is in series with Rs, right? Similarly, calculate lower cutoff frequency due to C3 alone. Due to C3 alone, and tell me. Lower cutoff frequency. Lower cutoff frequency due to see coupling. Why is it called coupling capacitor? Because it will couple the input signal, right? The capacitor will add to some DC value, and when you're biasing the transistor, your Vin is in series with the capacitor, so the capacitor will always couple it. Why we are calling it as parasitic capacitor? Why the name parasite? Parasite means I don't know what is a parasite, what is bacteria, virus, and all. Can you see a bacteria or a virus? No, is it not? But its effect is seen. Only its effect is seen, right? When you have a viral fever, you go to the doctor. The doctor, you repeatedly ask him, right? Why did I get fever? What happened? He says something is there in the air, right? So you can't see it, but still its effect is seen. Similarly, this capacitor is a parasite. Which one? Who is a parasite here? This junction. Wherever there is an N material, there is a P material, there is an N material, they will act like a capacitor, C pi and C mu. So it is a parasite. That C you cannot see. C pi, C mu you cannot see. It is a C, but you cannot see, right? But C1, C2, C3 you can see, right? Because they are physical capacitors. So anything that is not seen, it will create a problem in bandwidth. We are calling it as a parasite, right? Parasite. Lower cutoff frequency due to C3 alone. C3 alone. C1, C2 are replaced with short circuits. C3 alone. So here you have RC and RL. If you want, you can take R0 also, R0. So R0 and RC are in parallel. R0 and RC are in parallel. And you are seeing between the 2 points here. These are 2 points. Right? Capacitor left plate, right plate. Between the 2 points you have to see. So what is R equivalent? R equivalent is going to be R0 parallel with RC plus RL. So what is tau? Tau 3. R equivalent into C3. It is R naught parallel with RC plus RL. And what is omega 3? It is 1 by tau. Omega 3 is 1 by tau. It is 1 by R naught parallel with RC plus RL into C. So tau is R into C. So we have found three cutoff frequencies, lower cutoff frequencies. So out of these three, who is the cutoff frequency? Tell me, who is the cutoff frequency? First of all, which one has got the largest time constant? Or which one has got the lowest time constant so that it will have largest cutoff frequency? Omega is 1 by tau. Omega is 1 by tau. Wherever tau denominator is large, value will become small. Denominator is small, value will become large. Right? It's simple mathematics. So if tau is small, omega will be large. If tau is large, omega will be small. Right? Out of the three, which one has got a small tau with all the GMs and all that, with all the parallel combinations, no R naughts and no R pi's, and right, so very small tau, so that it will have the largest cutoff frequency. So out of the three, who's got GM? Because 1 by GM is the smallest value. So 1 by GM happens to be for C2. So this guy should be omega 2. This guy should be omega 2. You will have a omega 1 and probably omega 3 because of the R naught value. So R naught is large, R naught parallel RC plus RL into C1, right? Whatever it is. So omega 2, out of this, who is the best compromise here? If omega 2 is suppose 80 hertz, omega 1 is 20 hertz, and omega 2 is somewhere 5 hertz, like that. The best approximation is the largest one, the largest cutoff frequency you can take. So this omega 2, so we'll come to that later, right? We'll come to that later. So now we have just calculated due to C1 alone, C2 alone, and C3 alone, Now, all of you, if suppose the capacitor, if the capacitor is across RL, if the capacitor is across RL, then what will be R equivalent? If the capacitor is across RL, parallel, then RC parallel RL you have to do. You have to do RC parallel RL if capacitor is across RL. Capacitor is in between RC and RL, then RC and RL will come in series. So even if you inject some current here, the same current is going to flow through both the resistors. Whenever same current flows, then they are called in series. So R naught parallel RC plus RL we have to do. You should not do parallel to RL, right? Parallel to RL if you want, then capacitor you have to connect across RL. Then RC and RL you can combine, right? Okay. Now, which analysis is simple? The low frequency analysis or the high frequency analysis? The most easiest analysis is high frequency analysis, because in high frequency analysis, in a single step you can finish, provided you know a theorem called Miller's theorem. You know a theorem called what theorem? Miller's theorem. If you know that theorem, then directly in a single step you can finish high frequency analysis. But if you want to do by high frequency model, that also you do same answer you're going to get. In high frequency model, already the R pi, GM, V pi, R naught, you have to include extra 2 capacitors. You have to include extra 2 capacitors. That becomes the high frequency model, right? So high frequency analysis. This is the most easiest of all the analysis, right? Low frequency compared with low frequency, high frequency is dead easy. But you should remember Miller effect. Otherwise, this is the most complicated analysis, right? So from its complete extremes, you want to make it dead tough or dead easy. If you want to make it dead easy, then you should know something called the Miller's theorem. What is Miller's theorem? Miller's theorem. Miller's theorem states that if you have an ungrounded resistor or an ungrounded capacitor that is stuck between two nodes, 1 and 2. 1 and 2, this is C. This is C. You have V1 and V2. Then it is replaced by two capacitors here. One here, another here. What is the value of this? This is C multiplied by 1 minus V2 by V1. 1 minus V2 by V1. And what is this one? This is C multiplied by 1 minus 1 by V2 by V1. Where V2 by V1 stands for the gain. Stands for what? Gain. If the gain is negative, then V2 by V1, that factor, the capacitor is going to simulate positive value. If V2 by V1 is positive, then you are going to simulate negative capacitance. But here, common emitter amplifier, suppose it has a capacitor here, which is C mu. This is V1 and V2. We know V2 by V1, common emitter, the gain is going to be minus GMRC if input is given at base and output is taken at collector. So this C mu, you can replace it by two capacitors here. Two capacitors. What is this? C mu multiplied by 1 minus V2 by V1. And it is C mu multiplied by 1 minus 1 by V2 by V1. So do you remember this? If you remember, then we can go for an analysis called what analysis? High frequency analysis. High frequency analysis. This is something called Miller's theorem. It is called Miller's theorem. Okay. Miller's theorem. What is the spelling of theorem? T-H-E-O-R-E. Okay. So for high frequency analysis, C1, C2, C3 are short circuits. Then how the circuit will look like? It looks very, very easy now. Very, very dead easy now. Because no capacitors are there, right? Only RC, RL, here you have RB and RS. For calculating capacitances, tau, Vs is equated to 0. Now, where are the parasites? Where are the parasites? The parasites are, this is an N material, P material and PN material. A transistor has got two junctions. This is the parasite here. This is the parasite. Okay. So, high frequency model. High frequency model. If you want high frequency model, otherwise directly there I will do, right? So this is the high frequency model. You have C pi and C mu. C pi is called the forward biased diffusion capacitance. Diffusion capacitance. C mu is called the reverse biased transition capacitance. Transition capacitance. So to draw the high frequency model, already we know this. Am I right? R pi Gm V pi in parallel with R0. R0. Now, for this is base, emitter and collector. For this circuit, see where are these capacitors? Base, emitter, collector. Where are the capacitors? One is between base and emitter, C pi. C pi. The other is between base and collector, C mu. And now you have to connect all the resistors. If you want, then you can go bookish and do from here, right? That is one way of doing it, right? I will do here. I will do in this small space, right? Can you see small space here? This is enough for us to do the high frequency analysis. But if you want to draw the high frequency model, you can draw this and do it, right? But your answer is not going to change. Okay. So let us do here. For doing here, you should know Miller's theorem. Without knowing Miller's theorem, we cannot solve it. We cannot solve it. So what is Miller's theorem? Miller's theorem states that if an impedance, if an ungrounded capacitor is connected between two nodes V1 and V2, then it is replaced by two capacitances, right? Two capacitances. Here you have RC, RL. Here there is RB, and there is already C pi, the C pi, C mu, C pi. So who suffers with Miller effect here? Who suffers with Miller effect? C mu. It suffers with Miller effect. It suffers with Miller effect. Now, this capacitor, we are going to split it into two. One is C mu multiplied by 1 minus V2 by V1, right? And here one more capacitor here, C mu multiplied by 1 minus V2 by V1. This is 1 by V2 by V1. Okay. Now what is V2 by V1? Please tell me what is V2 by V1 here. This is RC parallel RL, V2, this V1. This is our common emitter amplifier. What is the gain of common emitter? The gain of common emitter V2 by V1 is minus GM into RC parallel RL. That value you can substitute. So you get C mu into 1 plus GM into RC parallel RL. And this is going to be C mu into 1 plus 1 by GM into RC parallel. This you can neglect because such a big value in the denominator approximate to C mu. It is approximated to C mu. Now, in a single shot, we can finish tau 1 here and tau 2 here. It is not two times we are going to do tau 1 and tau 2. What is tau 1 and what is tau 2? What is tau 1 and what is tau 2? For tau 1, for tau 2, because it's so zigzag, I will draw neatly here. Okay, we'll take a fresh page. RS, RB, C pi, C mu multiplied by 1 plus GM into RC parallel RL. This is approximately C mu. This is, there's only one capacitor, no? There's only one capacitor. Why did I draw two? Huh? One capacitor. There is nothing here. This is RC and RL. So now here you can get tau 2. Here you can get tau 1. So tau 1 equal to RS plus RB into C pi plus C mu into 1 plus GM times of RC parallel RL. And what is tau 2? It is C mu into RC parallel RL. So the total delay, first class you see, whenever you have shunt capacitors, I told you a statement in my first introduction. The total delay offered by the system is equal to the delay offered by individual poles. Individual poles. Then what is your upper cutoff frequency omega h is 1 by tau. It is 1 by tau. Can do it. That's all. But if you say no, sir, I want tau to be tau 1 plus tau 2, okay, you can do tau 1 plus tau 2. But tau 1 is nothing but 1 by omega h1 plus 1 by omega h2. So you can do this. Omega is simply 1 by tau. What is tau? Tau 1 plus tau 2. You just calculate tau 1 plus tau 2, add and do this. Now, out of tau 1 plus tau 2, if tau1 is much larger than tau2, if tau1 is much larger than tau2, then what happens? If tau1 is much larger than tau2, then omega h is simply going to be 1 by tau1, going to be 1 by tau. This is called the dominant pole. In the controls, we'll call it dominant pole. We call it dominant. Why am I saying it's dominant? Because you can see the factor C mu multiplied by 1 plus GM into RC parallel, big tau1. Tau2 is very small. So your upper cutoff frequency is the dominant pole, the 1 by tau1. That tau1 we can call it as dominant pole in control systems. In controls, they will call it as dominant pole. We will call it upper cutoff frequency. We will call it what? Upper cutoff frequency. So in a single shot, up. So slowly, intuitively, how you can do here? See here, tell me. Suppose amplifier is given. This is amplifier. Where is the high frequency model? Yeah, this amplifier is given, and you want to calculate the key frequencies. What you will do orally? This C mu is there. This C mu multiplied by 1 plus GMRC will be here. So the dominant pole is going to be C mu multiplied by 1 plus GMRC, C pi. And here your R pi, RB and RS are in parallel. Please see here, R pi I have missed. And I'm doing it fast, I'm doing it much better. Here there is an R pi which I missed here in this. All of you, who is this guy here? It's going to be R pi, right? So here we can have a RB, where is tau1? Tau1. RS parallel with RB, parallel with R pi. You can have RS parallel with RB, parallel R pi. But here RC parallel with RL. Two resistors are in parallel. You cannot add. You have to do it. Suppose all of you, you want R0 also. What you can do? You can have RC parallel RL, parallel R0 also. Okay. So this is perfect now. So here you have R pi, RB and RS. Here you have R0. So your tau1 is RS parallel with RB parallel R pi, C pi plus C mu into 1 plus GM into RC, right? So who is going to be the bandwidth now? Upper cutoff frequency or lower cutoff frequency? This is going to be your omega 2, omega 1, omega 3, right? Due to tau1, right? This is omega L2, omega L1, omega L3. Omega L2, omega L1, omega L3. This is due to C2, C1 and C3. This is omega H1, omega H2. Now, suppose if L1, L2, L3 are very close by, then what is the overall omega L? Suppose one is 2 hertz, 3 hertz, 5 hertz like that. Best approximation is you can add omega L1 plus omega L2 plus omega L3. You can add, right? You can add all of them, or this is approximated to omega L2, I told you. Why it is approximated to omega L2? Suppose if omega L2 is very large, 80, this is 80, this is 5, this is 4. 80 plus 5 plus 4 is almost 80. So omega L you get 2. But what is omega H? Omega H, if you want to know, then you have to calculate the delay. The total delay offered by the system is a delay offered by individual poles, 1 by tau. What is tau? Tau1 plus tau2 plus tau3. And what is tau1? Is 1 by omega H1 plus 1 by omega H2. So for upper cutoff frequency, you have to take, because shunt capacitors are there. This is like the impedances in shunt, right? 1 by omega H1 plus 1 by omega H2 you have to do for upper cutoff frequency. For lower cutoff frequency, you can add them, or you can have the best approximation, right? So what is bandwidth finally? Bandwidth is upper cutoff frequency minus lower cutoff. So in this, who is the best approximation? Best approximation, omega H1. Here, omega L2. Omega L2. Approximation, right? Approximated. Now, omega H1 is in megahertz. Omega L2 is in hertz. Megahertz minus hertz. So who is bandwidth? Is the dominant pole. Who is bandwidth now? It is a dominant. This fellow is bandwidth. But if you say, no, sir, I will do omega H minus omega L, okay, that also you do, but omega L2 is neglected. It is omega. So the dominant pole is the one who's going to govern the whole system, right? So that pole is the one who decides the speed of the circuit, right? In op amp, the slew rate of the circuit, when we take up a slew rate CMRR in our last topic, you realize that it is these capacitors, right? The dominant pole capacitors that are responsible for the speed of the device. The speed of the device is totally controlled by this. If you say, what about C1, C2, C3? Chota mota, right? It's like, I don't know. It's like in a Diwali, there are small crackers, right? Small red ones, right? And then there's one atom bomb, and then everybody blasts. So you'll hear only this guy's sound, right? So this is the whole system is going to get controlled by only this dominant pole. All other fellows are like naam ke vaste. They will be there, but they are not going to control the system slew rate or the system speed or the system bandwidth. The system bandwidth is totally governed by omega H1. That is the dominant pole. So finally, by seeing an amplifier, can you tell the bandwidth now? By seeing an amplifier, what is the bandwidth? If somebody says, just in 5 seconds, you have to tell the bandwidth. What is the best way? Just go and calculate the Miller capacitance. That's it. Just don't see all the capacitors. C mu is there. C mu at input is C mu multiplied by 1 plus A. So there you are having C pi plus C mu multiplied by 1 plus A into RS parallel RB. Are you getting? So the dominant pole capacitor is, are you getting? So if you want to calculate what is the dominant time constant, the dominant pole. So what is the best way? Then you are having a transistor here. Here there is C pi, and here there is C mu multiplied by 1 plus A, where the gain is, and here you have RS, and this is RB, right? Or RB RS. Here they have R pi. So simply tau is RB parallel RS parallel with R pi into C pi plus C mu multiplied by 1 plus A. What is bandwidth? 1 by tau. That's all. This is the summary of the discussion. The whole summary says that you want to calculate the bandwidth, just go and calculate the Miller capacitance effect. Miller's effect is not seen at output side. It is more pronounced at input side. At the output side, it is C mu multiplied by 1 plus 1 by A. C mu multiplied by 1 plus 1 by A. Is it not? Where A is GM times of RC parallel RL. If you want R0, you can include R0 also. So you can substitute here. This is the bandwidth. So this is an approximation. Are you getting? The moment you see an amplifier, say, don't do anything, just go and tell the bandwidth orally, right? Now, how to decrease the time constant and improve bandwidth. And improve bandwidth. How to decrease the time constant and improve bandwidth. Now, what if I make this A? Can you see C mu multiplied by 1 plus A? I want to make that A as 1 because the least gain that you can get in amplifier is 1. If I make it 1, then it is C mu multiplied by 1 plus 1. It is going to be 2 C mu, and the whole time constant will shrink. Once the time constant shrinks, the bandwidth of C amplifier will improve. So if you want to make this as 1, then you have to, if you want to make it 1, then there should not be, what should I say? There should not be RS and RL here. Suppose instead of RS and RL here, if I have another BJT like this, where the gain is 1 by GM, where the time constant alpha by GM or 1 by GM here, then what will be A? What will be A? Then A is going to be minus GM into 1 by GM. What is minus GM into 1 by GM? It's minus 1. So minus of minus here, right? So that the mod A is going to be 1. So if you substitute 1 here, it becomes 2. So that technique we will do, but not now, right? So this is called cascode. This is called a cascode amplifier. In cascode, very simple, that RC, RL at the output is there, no? Instead of RC and RL, we are going to put a common base amplifier, and we are intentionally going to decrease the gain of the amplifier. So how to decrease gain, how to decrease the time constant and improve bandwidth, right? To decrease the time constant and improve bandwidth, you have to decrease the gain. So how to decrease the gain is, next stage, if you put a common base where the input resistance is alpha by GM, then definitely we can decrease. That is one thing. So we will go there, cascode. But before that, one more question. Question is, if somebody asks you in an interview, why Miller effect is not seen in CB and CC. Why Miller effect is not seen in CB and CC? Why it is seen only in C? Why Miller effect is not seen in CB and CC? So let me draw CB here. CB. In a CB amplifier, base is grounded. You have C pi here and C mu here. So what is the answer for this? The answer for this is, Miller effect is not seen for grounded capacitors. Grounded capacitors. This is something I've told you in my first class, right? Miller effect is not seen for grounded capacitors. So this is CB. This is CB amplifier. This is grounded. And where is this C pi and C mu? Base, emitter, collector. So between base and emitter, there is C pi. Between base and emitter, oh, base and emitter, C pi. Between collector and emitter, C mu. Can you see how lovely these capacitors are connected to ground, common base? So there is no Miller effect, no Miller effect, no Miller effect. Miller effect is not seen for grounded capacitors, grounded resistors. Miller effect needs an ungrounded, where there is a V2 and V1, where there is a V2 and V1, right? But here one of the terminal is connected to ground. No Miller effect for CB, common base amplifier. What about CC amplifier? Common collector. In a common collector, collector is grounded. Collector is grounded. This is emitter. This is base. Common collector. Input is given at base, output is taken at emitter. Where is capacitor here? Here there is a capacitor which is, okay. I think till now we have not drawn common collector like this. No? We have always drawn like this. Like this, and this is collector is connected to supply. I think now you are comfortable. This is V in, V naught, emitter follower, output follows input. Output follows input. Now, where there are capacitors, one is C pi, the other one is C mu. C pi and C mu. Collector is common, collector is grounded, C pi, C mu. Am I right? Now, no Miller effect here, no Miller effect. Why there is no Miller effect? Because one of the terminal of capacitor is grounded, it is grounded. But what about C pi? What about C pi? Now C pi is connected between V in here and your V naught is V in. The gain is 1. And here you have connected a capacitor. Now, first of all, when the potential difference is same, when the potential difference is 0, what will be the current flow through the capacitor here? The current is 0 because V naught and V in, if you apply any signal, the dynamics here and the dynamics here are same. Then what will be the signal current between the two terminals? The current is 0. This capacitor experiences bootstrap. Experiences bootstrap. Did I tell you? Whenever you find a bootstrap resistor or capacitor, first class I told you, don't consider such elements. Don't consider them. Just think that they are not there. Right? If somebody says, is there C pi? They say, no, C pi is not there. Why it is not there? Because the current flowing through an element is 0. This is like a diode in reverse bias. If you have a diode and it's reverse bias and there's no flow of current, what will you do? You'll replace the diode by open switch, am I right? So similarly, no current is going to flow because one capacitor is having no Miller effect because one of the terminal is grounded. The other capacitor, there is no question because the potential difference is 0. So when the potential difference is 0, so there is no question of what? Miller effect at all. Miller effect is not seen in CC and CB. So what is the gain? If you want to calculate the gain of the input capacitance C, it is C multiplied by 1 minus V2 by V1. Am I right? So it is C multiplied by 1 minus 1, that is going to be 0, right? So if you want, you can calculate. Otherwise, same potentials are there, no current. When there is no current, then it is 0. It is going to be 0, right? So C multiplied by 1 minus V2 by V1. This is V1. This is V2. So it is 1 minus V2 by V1, it is 1 minus 1, it is going to be 0, right? No Miller effect for no Miller effect in common collector amplifier. Miller effect is seen only in common emitter amplifier, right? Common emitter. That too only one capacitor, that is between the base and the collector, only one capacitor. The other capacitor, C pi, is however grounded when your emitter is grounded. Okay, so how to improve bandwidth? How to improve bandwidth? right? By decreasing time constant. How to improve bandwidth by decreasing time constant? Two methods are there. One is the answer for this is connect a voltage buffer at input or a current buffer at output of C amplifier to improve bandwidth. Connect a voltage buffer at input or a current buffer at output of C amplifier to improve bandwidth. What is this statement? Connect CC here or CB here. CC is a voltage buffer. CB is a current buffer. CB is a current buffer. If you connect like this, then you can improve, then you can decrease the time constant tau. Now, if you ask me how to decrease the time constant, think about it. How? Simple. Now, this C amplifier, what is the input resistance of C and output resistance of C? Here it is R pi. Here it is R naught. Then how to decrease this R pi is, if I connect a common collector here, a CC amplifier, then this is going to be alpha by GM. The overall tau, what is the overall tau? Alpha by GM parallel with R pi. Alpha by GM parallel with R pi is approximated to alpha by GM. So 1 by GM is 100 times less than R pi, right? Alpha by GM is suppose 10 ohms. R pi is say 10 kilo ohms, right? Or 1 kilo ohm, 100 times more. So what happens if 10 ohms comes in parallel with kilo ohms? It is 10 ohms. So if R reduces, if R equivalent reduces, tau will reduce and bandwidth will improve. Because common collector output is emitter terminal, Common base input is also emitter. Common base input is again emitter. If you connect common base here like this, common base will say, don't worry, R naught is there. This is alpha by GM again, alpha by GM. What is the overall effect? Alpha by GM, right? So R equivalent reduces, tau will reduce, bandwidth will improve. So it's a simple technique that whenever you have a common emitter, when the common emitter sees left side like that, there should be an emitter terminal. Right side is the emitter terminal. Emitter means alpha by GM, emitter means alpha by GM. Which configuration output is emitter? Which configuration input is emitter? Output is emitter is common collector, input is emitter is common. So if somebody asks you in an interview, how to improve bandwidth? If you tell him this side emitter, that side emitter should be there, he will not understand. That is a technique, but he will pull his hair, right? What is this emitter, this side emitter? So you should say in a little, technical way, stylish way, like an educated person, you have to tell. So how will you tell? Connect a voltage buffer at the input or a current buffer at the output. That fellow will get worried. Wow, this fellow knows a lot of electronics. But we know that when you connect voltage buffer at input, the output is at the emitter terminal. So you are getting low resistance. Similarly, the current buffer at the output, a voltage buffer at the input, current buffer at the, who is a current buffer? Common base. And common base input side is emitter only. So when you have input emitter, naturally the R equivalent will reduce. tau will reduce, bandwidth will improve. So next time somebody asks you, don't say left side emitter, right side emitter. What you should say? Connect a voltage buffer at the input or a current buffer at the output to create mismatch between the two stages, and the overall time constant will reduce and bandwidth will improve. If you say like this, this fellow knows, yes or no, right? But you and I know that this should be alpha by GM, right? That's a simple thing, right? So there's a summary. You read 10 pages of this cascode amplifier and all that stuff. Finally, you'll come to that conclusion, right? The alpha by GM parallel with RPi is alpha by GM parallel with R0. So you need a current buffer at the input side or output side, and a voltage buffer at the input side. Okay, we'll stop here. Tomorrow we are going to give this combination to decrease the bandwidth, right? So now
Yes, sir.
your doubt.
Hello, sir.
Yes.
So page number 10.
Yeah.
MOSFET telescope.
Yeah.
Sir, actually I'm quite confused. Can you just tell Rx?
What is Rx?
So Rx is the output resistance with respect to M2 and M1.
No, yesterday's class, you see that there will be two MOSFETs like this.
Yes.
Okay. Here there is suppose R01, R02. And you want to find R0 here. You see yesterday's class. There's R02, there's R01. What is R0? R01 plus multiplication factor. 1 plus GM1 into R02.
Yes, so I was thinking if we have to include this in the denominator also with respect to.
No, your input is applied only to Q1, no? So only 1 by GM1 will come.
Okay, there I was just thinking.
See, suppose your input is applied at the upper transistor with respect to ground. Then
we
only the lower transistor input is there, no?
Yes, sir.
Okay, I'll do one thing. I'll do the same problem in a different method later.
Okay, sir.
Okay.
And in the last slide, sir, which you are explaining.
Yes.
The Miller capacitance. So, first suppose if we include R0 in the CC amplifier, then first suppose
the CC amplifier.
Yes,
R0 will come in parallel with alpha by GM, no?
That's it. Right? I mean, we will be considering if there is a early effect. We will be considering.
Early effect is there. It is waste of time because R0 parallel with alpha by GM is still alpha by GM only. No?
It will be in some
ground, my dear.
Yes, yes, sir.
R0, no?
Yes, sir. Got it, sir. That's it, sir. Thank you, sir.
Hello, sir.
Yep.
Hello, so 35F.
Yeah.
So here, how did we calculate that C equivalent? You taught that method now that we have to see through one capacitor or some.
Yeah, there is already a capacitor here, no? C mu.
Yes, sir.
The parasitic capacitor. That we are splitting it into two capacitors. One here and one here. That we have done here.
So where are we seeing this C equivalent from?
C equivalent is nothing. C equivalent, acha, you want. So the complete capacitors, you have to combine them first. You have to combine them. It becomes one. And then between the 2 points, you have to see. So let me draw it here. RS, RB, or RB, RS, whatever. Here, capacitors are there. Here you have to see. These are the 2 points. Here there is R pi. So it is between the 2 points you have to see. You have to remove the capacitor and see.
Okay. And also, sir, 38F, I didn't understand that how to improve bandwidth.
Yeah, to improve bandwidth, we have to decrease time constant, I'm saying. What is time constant? R into C. So what is R here? Here there is R pi. Here there is alpha by Gm. Overall equivalent is alpha by Gm. Tau will reduce, no? Here it is R naught, common emitter, output. Here it is alpha by Gm. Overall is going to reduce, no?
Okay.
Are you getting?
Yes, sir. Yes, sir.
Yeah.
And also, sir, I have a small request. Hello?
Yeah.
I have a small request, sir. While we are asking doubts in doubt session, all the participants are muted at once, and the one who speaks the loudest gets the first chance, even though it's not their chance. So
Oh.
if
No, any suggestion you want to give, I will talk to
the
because
mute, yeah, I just wanted to let you know that if we could mute the participants one by one, then that would be more sufficient. Otherwise, the person who shouts the loudest gets the chance to talk and solve that first, and
yeah,
that who gets disturbed.
you unmute one by one, please. Venkat, please unmute the participants one by one.
Hello,
Each
sir.
one. Huh?
So I had a doubt, sir.
Yes, tell me.
So in when you were discussing low frequency analysis, in that the C3 alone, so the previous the RB and RS, what happened to those two, sir? That I didn't understand.
RS,
Why did-
RS and RB.
RS and RB.
Yeah,
we
for
didn't
this
consider
I have
those two.
already given an explanation. I told you any day you get a doubt when you are looking at collector, what will happen at base? Then you have to draw the small signal model like this, I told you. This collector, this base. Here those resistors will be there. So there is no connection between collector and base. Here there is R0. Here you have RL and RC. This is RB and RS. Are you getting?
Yes, sir.
R pi. There is no connection between base and collector.
Okay, fine, sir. Now, sir, one more doubt I had, sir, was that right now, we are taking capacitors in between of all the BJTs.
Yeah.
And previously, when we were taking diodes, so in which question, like, how do we know in which question do we take consider diode or a capacitor? That was kind of that I didn't get.
You want to
grasp.
consider it. No. Capacitor, if the examiner asks you frequency, cutoff frequency, he will give capacitor. But diode 0.7 volts is only for DC analysis. And resistor, if you put, it is AC analysis. The examiner has to give a millivolt signal like that. The moment he gives a millivolt, you understand that it is small signal. If he gives 5 sin T, 10 sin T, it is normal sine wave. Then you can do rectifiers.
Okay, sir. Fine, sir.
Are you getting?
Yes, sir. For
Diode
frequency
is there,
analysis, only
10
then
sin
we
T,
use
20 sin
capacitors.
T, 230 volts is given to it. Then it is okay, your rectification. 2.5 sine omega T millivolt means millivolt sine wave is giving. That means small signal analysis. No?
Okay, sir. Fine, sir.
Yeah.
Thank you, sir.
Hello, good evening, sir.
Yes.
Sir, could you open 30 or 31F, sir, so that low cutoff frequency by C3 alone?
Yeah. This one C3 alone.
Sir, here I wanted to, sir, 29F, sir, once. Sir, here for calculating R equivalent, you took means like till just R naught, but the right side of RS and RB, that part, sir.
Right side of RS and RB. Where is?
So 30F only, 30F you open once, sir. Here, sir, we considered R naught and RS and RB that are
That is
connected to the
exactly
base.
what the previous student was asking me doubt. There is no connection between collector and base, no?
Oh, okay.
Connection ही नहीं है. See, base terminal. I don't know. You are from which place?
Sir, Kolkata, sir. I get both English and Hindi. No issues, sir. You can tell in any way.
कोई बात नहीं. तो ये base if it is at what you call railway station collector is near Kalimata Mandir, like that.
Okay.
Are you getting?
Yes, sir. Understood.
Okay.
Sir, one
Good. Yeah.
second doubt is in 9F, sir.
9F. Yeah.
Sir, I have a minor doubt in this. Means like in this circuit,
See,
when
I
you take
told
this
you
loop,
already, there is no doubt that is minor, because you have seen most of our problems we have solved only by voltage division rule.
Yes,
So
sir,
you
yes,
can
sir.
ask me any doubt, any minor doubt that is there. I don't consider it as minor. Okay.
Sir, then, yes,
You
sir.
can ask me anything you wish.
Sir, here this, sir, that loop you take, na, sir, this I am not getting. Means every time you take this loop, sir, that single current.
This one, no, you do one thing. Vn equal to, you write VBE plus IE into 475 plus IE into 475 plus VB equal to 0. Can you do like that, Kirchhoff's law?
Yes, sir.
And you take IC common. You know VB equal to IC into 1 by GM. You take IC common, then you'll write 1 by GM plus 475 by alpha plus 475 by alpha. Can you do like that?
Okay.
What is there
Yes,
one
sir.
extra equation you have to write? That's all. Yes or no?
Yes, sir.
Suppose
Yes.
a transistor is there. How we started basic, you have to see. From where I got this idea, right? See, that is a problem. After getting the shortcut, from where we have got that we are forgetting, no? Vin equal to VBE plus IERE. Am I right?
Yes, sir.
So here IC we have to take common. When you take IC as common, then this will be 1 by
1 by
GM
G.
plus RE by alpha you will get. This is V. Then V naught is again minus ICRC. V naught is minus ICRC. Are you getting?
Yes, sir. Yes, sir. Yes, sir.
So V naught by Vn is
Yes, sir.
minus RC by 1 by GM plus RE by alpha.
By alpha.
Can you see? What is there? One Kirchhoff's law you have to write here. Some students are saying, sir, last 2-3 days you are writing this directly. We are getting difficult. What is there? One, if you have problem, can't you write one Kirchhoff's law for output loop and input loop?
No,
One
sir.
small equation if you write, same current numerator, same current denominator. That's all. What is there?
Okay. No, sir, I was writing in different current, because of that I was getting means like.
Then that is why basic Kirchhoff's law you go. From where did I get this voltage gain? You see, numerator base current, denominator base current, one method. Numerator collector current, denominator collector current, another method. Numerator emitter current, denominator another current, emitter method. Are you getting?
Yes, sir. Got it. Thank you, sir. Thank you very much.
Hello, sir.
Yes.
Yes, sir. I was asking, sir, in the last high frequency,
Ah.
in the Miller effect, if we take resistance in emitter, so our gain will become RC parallel RL upon 1 upon GM plus 1 beta plus 1. Oh, sorry.
No, which page is that?
Sir, sir, high frequency Miller effect when we
This one?
high frequency analysis. Yes, sir.
Yeah, tell me.
Sir, if we take emitter resistance also, sir, then the
Where is emitter resistor?
no,
yeah.
if we take, if we take
Okay.
emitter,
Very good. Tell me. Then you
if
have
we
to do, instead of R pi, you have to write R pi plus 1 plus beta times of R. You are right. Absolutely
sir.
right.
Sir, one more doubt I have. I have asked you on WhatsApp that doubt, and I'm still not able to clear that doubt. You
Tell
said
me, what
in
is that doubt?
multi-stage, that will be covered in multi-stage. That V naught by Vx into Vx by Vn.
Yeah, that today we have covered, no?
Yes, sir. But in
Today
that we have.
this one, no?
Yes, sir. But instead of in it,
This is RC.
yes, sir.
Your doubt was this. Here there is R2 there. Am I
Yes,
right?
sir. Yes, sir.
Okay. Yeah. Let me do it for you. What is there?
Yes, sir.
Just observe. Huh?
Yes.
Can you see my screen?
Yes, sir.
V naught by Vs is V naught by Vx into Vx by Vs. Am I right?
Yes, sir.
V naught by Vx is common emitter, no? Any
Yes,
problem? You just
No, sir.
close your hand or you draw it separately like this. This V naught, this Vx. What is V naught by Vx? Common emitter. What is the common emitter? Minus GMRC. Minus
Yes.
RC by 1 by GM. Am I right?
Yes, sir. Yes.
Now you have problem with Vx by Vs.
Yes, sir.
But the input resistance here is R pi, no? In multi-stage, when we are going for next stage, you have to calculate the input resistance.
Yes, sir.
So here there is R pi.
Okay.
So this is
okay.
a simple voltage division formula.
Now
So
I
it
get
is
it.
R2 parallel R pi by R2 parallel R pi plus R1.
Yes, sir.
Are you getting?
Yes, sir.
Yeah,
I was not considering that R
Yeah,
pi.
I can see a smile on your face from here. Okay.
Yes. Thank you, sir.
Right, right.
Hello, good
Sorry,
evening, sir.
8.
8F.
Yeah. Yes.
Sir, in both I are in opposite direction or in the same direction.
This I same current source. Two current
Then-
sources we have connected.
Then there won't be any current through RE, right?
There won't be any. Yes, yes. You're absolutely right. The DC current won't be through RE. AC current will be there.
Okay, sir. Yes.
You're right.
Yes, sir. Thank you.
Okay.
Good evening, sir.
Good evening.
Sir, actually, yesterday only I joined the class. So the concept of differential amplifier I understood, but when the problem I can't able
Okay.
to
Yeah.
revise
You
all
have.
the previous,
Yeah. I mean, do you have notes of previous last
Yes.
4 days?
last 4 days. No, actually, from day one itself, I didn't.
Yeah, I can understand. You have joined yesterday, no?
Yes, sir. Yes, sir.
Yes. Last 4 days notes you take.
Okay.
Go
sir.
through them from beginning. You go through them. Okay.
Okay.
You
sir.
do you have my WhatsApp number?
No, sir.
Okay, I'll give you.
Okay.
If you have any doubt, just go through. You mostly will understand, but because without studying anything, directly joining yesterday, you have understood differential amplifier means. Once you go through, I hope you might get some idea.
Yes, sir. Actually, I can able to understand the concept, but when the problem is coming,
Yes,
some
because no practice,
factors
no.
are coming.
Only yesterday you have joined. There is no practice. First DC analysis class you have not attended.
Yes,
IC
sir.
equal to beta IB, basic small problems. So you
Okay.
please refer last 4-5 days class,
Okay,
starting from BJT.
sir. Okay, sir.
Okay. So my phone number you can note down.
Okay, sir.
Can you see on a screen?
Yes, sir. Able to see.
Yeah. You are from which place?
Sir, I'm in Singapore now.
Oh, okay.
Hello, good evening, sir.
Yes.
Sir, I had a doubt in final page. You told about Miller effect. There is no Miller effect in common collector and common base.
Yes.
So, I mean, these Miller effects are for high frequency analysis, and then if there are no Miller capacitances, then does that mean that tau will be 0 and there will be infinite? I mean, there will be like low pass behavior. It is.
Yeah. See, our main aim is to have a low pass emitter. Our main aim is to get, but there will be an upper cutoff frequency. Yes or no?
Yes.
Definitely. See, if you don't have one capacitor, you have other capacitor also, no?
C pi is there, sir.
So naturally that will have to affect some time constant.
Okay. But here, for example, in common collector, C pi got cancelled due to this Miller 1 minus V2 by V1, and C mu is directly grounded. So there is no capacitor in the high frequency analysis.
See, the question is, Miller effect will not eliminate time constant. Miller effect will decrease the time constant. There is a difference. Some capacitance common base amplifier is said to be a high frequency amplifier because time constant is low, because it's not, there is no multiplication of 1 plus A.
Yes.
So capacitances will be there. Yes. If you want infinite speed in an amplifier, then maybe, someday a student like you who's working in an organization, he might think of changing the whole, what you call device itself. So you should think of a device that has no junction at all in it.
Okay.
Because all this problem has come because the devices have junctions.
Yes,
That is the biggest headache for us.
Yes, sir. PN
So
junction,
someday
that is.
might come out with a device like that, where there is no junction at all. then there won't be any junction capacitance. Then we might have, our laptops and all that running with infinite speed.
Yes, sir. That's okay. Thank you very much, sir. Thank you.
Yeah.
Hello, sir.
Yes.
Page number 17.
Yeah.
Sir, in this first with respect to base RE parallel with R pi naught by alpha, only in previous problems we take the denominator, sir. You take with the numerator also, guys.
You want to take RE
By
parallel R pi only in the numerator?
No, sir, by alpha.
Yeah, because the emitter current, numerator is collector current, denominator is collector current we are writing. No? But here actual current is emitter current.
In previous problems, this problem, only denominator we take, no, sir. You take
No. Numerator alpha. Yeah, because in common emitter, output is taken at collector, no?
Okay, sir. Both
output is taken collector resistor, you can't take alpha, no? What is there? You write one equation. Here, see here. Vx, you write like this. Vx equal to IE into RE. Can you write?
Yes,
In equal to VB plus IE into RE. Are you getting?
Yes, sir.
Then what is Vx by Vn? Vx by Vn. Like this. So Vx by Vn is numerator current should be IE, denominator current should be IE. So if you take IE common, it will be RE by or IC. Numerator IC means RE by alpha by IC 1 by GM plus RE by alpha you will get. Are you getting?
Okay, sir. We taking output at emitter means both will come.
Yes. You're right.
Okay.
Yeah.
Hello, sir.
Yes.
In low frequency analysis, we take along with C1 only, other we can take C2 or C3, sir.
We can take with C1?
Only we can take along with C1 only. C2 and C3 we can also take on.
Yeah, examiner will give only one capacitor, C1 alone, or in some gate problems, C3 alone. In some gate problems, C2 alone. Only one capacitor is giving. But if you want to find overall means, we have to calculate all the three and lower cutoff frequency, whichever is the highest. Highest is omega 2, no? That is the cutoff frequency. Yeah.
Sir, can you please explain about the coupling and bypass capacitor, sir?
Coupling and bypass, you have joined yesterday, huh?
No, sir. That name I didn't understand, sir.
Hello? See here. A coupling capacitor, suppose I have some voltage here. This is your input signal in millivolt. This is 4 volt or 0.7 volt or 4 volt, you can take 4 volt. Then this, because of this 4 volt, the DC, the diode is on, no? So at the input, there is a DC coupled with AC. Coupling means adding the 4 volt DC with Vin is there. Then the device is on. But in self-bias, you don't have DC voltage. There is a voltage divider. There is a voltage divider like this. Suppose this is 10 volt, right? So if I put 6K here, 4K here, then you have 4 volt here. Yes or no? 4 volt. This we will store in a capacitor like this. Then this complete 4 volt will appear here. You can couple a signal here, Vin. Then the function of this circuit and this circuit both are same. Are you getting?
Yes, sir. Okay.
So you are coupling an input signal with a DC. That is why it is called coupling capacitor. Bypass capacitor is to bypass RE. Because if RE is there, gain will reduce. So if you put this capacitor, for AC analysis, it will act as short. The gain AV is going to be minus RC by 1 by GM. This is without RE. If you have RE, it will have minus RC by 1 by GM plus RE by alpha will be there. RE by alpha. So naturally the gain is now going to reduce. The gain is going to reduce with Re. Alpha is almost 1. So Re is called gain reducing resistor. So if you put capacitor, then it will bypass Re and the gain will increase from like this. Re will become 0. Are you getting?
Yes, sir.
Yeah.
Sir, once explain the parasite capacitor also, sir.
Parasite means junction capacitor, that's all. What is there to explain? Wherever there is an N material, there is a P material, there is an N material, there will be a junction. One plate is positive, other plate is negative. So there will be a small capacitance. That small capacitance will create a problem. The device capacitance is going to decide the bandwidth of the amplifier. But if that capacitor is ungrounded, if that it is still creating problem. A chota capacitor will behave like bigger capacitor because of Miller effect. Miller says that if you have an amplifier, this Vin, if your output is minus 2 Vin, and you connect a resistor R here, R, then what will happen if this is Vin, this is minus 2 Vin? When I give 0 to 1 volt here, 1 volt, the output is going from 0 to minus 2 volt. Then the current I will increase 3 times. Vin, I is Vin minus of minus 2 Vin by R. If the current increases 3 times, then the resistance is going to decrease by 3 times. Inductance is going to decrease by 3 times. Capacitance is going to get multiplied by 3 times because of Miller effect.
Okay. Sir, and another doubt, sir. In bypass coupling, bypass capacitor, if the output is both DC and AC, then bypass allows only DC or AC, sir?
By capacitor will charge to DC and it allows AC.
Okay.
Capacitor will charge fully to DC. Whatever is there,
AC.
it will allow. It will act like short circuit for AC. See, it's simple.
Okay.
Can you see the screen? Can you
Yeah,
see
yeah,
the
I'm
screen
seeing,
here?
sir.
Yes or no? Now,
Yeah, I'm seeing,
suppose I'm having 4 volt here. I'm having 3 volt here. So there are 2 stages of amplifiers. Now the challenge is, I have to block this 4 here and this 3 here. Both should be there. You have to block these 2 voltages. Then also you can use a capacitor here. If you use a capacitor, this capacitor will charge to 1 volt because 4 minus 3 is 1. So whenever he charges to 1 volt, he separates both the nodes by 1 volt here. This will always be 4 blocked here. This will always be 3 blocked. Can you see?
Yes, sir.
But if you apply a signal here, same signal will come here because he acts as short circuit for AC.
Okay, sir.
So signal will be allowed. DC at left side, right side, he will block. He will say, suppose Q1 transistor says, I want 4 for my collector base junction to get reverse bias. I want 3 for forward bias base emitter junction. Somebody block these voltages. Capacitor will say, don't worry. I will come in the middle. I will see my left plate is at 4. My right plate is at 3 here. I will block the 2 voltages. So 4 is at this plate. 3 is at this plate. But if you apply
Sir, AC signal will be allowed as it is, no, sir?
Now you got it. AC will be allowed. DC will be blocked. That is why these 2 lines. These 2 lines says that this voltage will be here at left plate. This voltage will be at right plate. Potential difference will be 1.
Yeah, sir. Yeah, I got it, sir. Thank you, sir.
Yeah.
Sir, if Miller effect is not seen in common base and common collector, how to calculate a high frequency analysis, sir?
Yeah, I will do. Tomorrow I will do. We have done only for common emitter, no?
Yes, sir.
Tomorrow we will do for cascode also. Common emitter with common base I will do tomorrow. Okay?
Sir, one more doubt. Sir, there are thousands, hundreds of transistors in an IC. So,
billions.
Yes. So, if all work together, then why don't we see Lenz law current? Like there is some induction current.
Yeah, definitely effect will be there. Definitely effect will be there.
How
We
do
have
they
to
reduce
calculate
it?
those values also. The VLSI tool is going to calculate every wire it will take. Wherever two wires are there separated by dielectric, there is a capacitor. It will model. It will model and calculate the delay and give you. Yes. A tool will do. Human intervention will not be there. As human beings, we cannot do. Yes, sir?
Yes, sir.
Yeah. Tool will do. Definitely tool will do. It will give every information.
Does it affect much, or how does it affect, sir?
It is definitely going to affect. See, what is VLSI finally is an inverter. If a student understands how the behavior of inverter is, one inverter, and all the parasitic elements in it, he can extend that inverter, because finally all the bigger gates, larger perspective, you are going to get only from an inverter. So when you study on book, on paper, it is only one inverter. Slowly we will combine those capacitors. Tomorrow I will take a 2-stage amplifier, and we are going to have around 15 capacitors in it. Are you getting?
Yes, sir.
So first there are 2 capacitors, right? The 2 has split now, coupling capacitor and all that. Tomorrow we will extend multiple stage. Tool will do, with a click of a button, tool will combine all the capacitors at one node, all the capacitors at other node, and calculate the tau and give the delay.
Okay.
Are you getting? It is only at that particular node, R you have to calculate, C you have to calculate. Tool can very easily do the calculation of R and C at every node. Suppose in a circuit, there are only 10 nodes or 5 nodes. There might be 100 capacitors, so what, 1000 capacitors, but they are only 5 or 10 time constants. Yes or no?
Yes, sir.
Because everything is going to come in parallel. So at every node, it will calculate and give you the delay. What is there?
Okay, sir.
Yeah.
Thank you, sir.
Yeah. Tomorrow I will do for 2 stage, then you will understand. Okay.
Yeah, sure, sir.
Yeah. Next.
Hello?
Yes.
Yes, sir. Can you go to that how to improve bandwidth last you were explaining? How to improve bandwidth by decreasing. Yes, sir. With CC and C connection, I have understood that how alpha pi GM plus R pi, sorry, parallel with R pi R came, but CE and CB I didn't understand.
C and C, yeah, tomorrow I will do this. CE with CB is cascode. The common base amplifier input resistance is going to come in parallel here, no?
Okay, you have written R0. I have written R pi and I was thinking that
No, you are right. R0 is correct.
Yes, sir. So, and yesterday you draw a circuit where it was CD and yes, sir, it was acting as CD and CS both, MOSFET MOSFET circuit.
Yeah.
So there, how it was working at CD, like CD, I didn't understand.
Which page?
So yesterday it was before that, so I don't know the page number. Yesterday.
You send me on my WhatsApp. I will see.
Okay, sir. So can you open last?
Yesterday.
There will be yes, sir. Before differential amplifier.
Background.
So if the BJT is in cutoff or saturation, then we cannot find the AC analysis.
What is this noise coming? Yeah, tell me.
So I'm asking that if BJT is in saturation or cutoff, then we cannot find the AC analysis.
Yeah, obviously, yes.
When it is working.
Amplifier means it has to be in active region.
Okay, that means we need not check.
No, there is no point. See, it's like doing analog analysis on a digital circuit.
Oh.
So logic 1, logic 0 is only digital, no?
Yes, yes, yes.
Yeah.
Yes, sir. Go to last before differential amplifier.
Oh my God, what is the sound is that?
This one? Differential amplifier.
Yes, yes, one.
Yeah.
Yeah, yes, I think. Says there's some kind of disturbance.
Yeah.
Oh, wait.
Yeah, tell me.
So there was a question where two MOSFET was in parallel and below that two MOSFET was in series, V01 and V02. Do you remember that? Before differentials. Yes. So just before this. CD, you're saying CD. Yes, sir, this one.
Yeah.
So here, like how is it a common drain? How
Common drain. Yeah, if you take output here, it is common source. If you take output here, it is common drain. Input
So
here. Where is input given? Gate. Output is taken at source. That is why it is common drain. Input is given at gate, output is taken at drain, common source.
Okay, sir. So, and if we will take that V01 by Vm, then we have not considered R01 and R02.
V01 and?
V01 by Vm. So there you have considered that output resistance, that early effect resistance of M3 and M4, but you have not
If you want, you can consider also. But what I'm saying is, if you consider, then what will be the resistance? It is R01 plus 1 plus GM1 into R01 into R02 will come. No? That will come in parallel with that. It's very large value parallel with small. It's not needed, I'm saying.
So, but you said now when there are only active, then we have to consider that.
Active is again with a multiplication factor, no? 1 plus GM or not. If you want to consider what is there, R03 parallel with 1 by GM4 parallel with R04 in parallel with, here can you see? Here in parallel with, again this R01 parallel with, so much why not needed.
Okay.
R01 plus 1 plus GM1 R01.
Yes, sir. And in differential amplifier, you said that one potential will be negative and one potential will be in positive.
Yeah, left side it is negative, right side it is positive.
So it will always be left side will be negative.
Yes, because left side is common emitter. Yes. Left side is negative.
Okay, because it's common emitter. Means if we will be asked that find that left side VC1 by
minus GMRC by 2.
Okay.
Right side plus GMRC by 2.
Okay, so one more time.
Hello, sir.
Yeah, next.
So you said something about we have to consider VA is equal to infinity for passive resistors. And actually once explain that, sir, I couldn't understand that one.
Passive resistors, sir. No, if examiner gives VA, then you have to consider R0, that's all. Acha, whenever passive resistors are there, in parallel with this R0 is there. Passive resistors are in kilo ohms, no? You cannot create a mega ohm resistance. Suppose a mega ohm resistance is there, passive element. If a milliampere current flows, the drop will be 1000 volts. Can you get a 1000 volts VCC?
Okay.
It's not possible. So all our resistors will be in kilo ohms only. If R naught, the dynamic resistance of BJT R naught is in mega ohms, kilo ohms parallel with mega ohms is kilo ohms only. There is no need for us to consider early effect. That is why examiner will not give early effect most of the problems. But if there are transistors with transistors, he might say in MOSFET R not consider. In BJT, you see, there is no problem in BJT where he will consider early effect. Are you getting?
Okay. So.
Yeah. Next, anybody else? Anybody else?
ಬರ್ತೀರಿ ತಡಿ ಆಗೋಯ್ತು.
Yes.
Hello?
Yes.
Yes, sir. In that high frequency analysis, we found omega H1 and omega H2, right? And where omega H1 was lesser than omega H2.
Yeah.
So then why is it dominant pole?
Because omega equal to 1 by tau. Tau is in the denominator. Tau is small, omega will be large. Tau is large, omega will be small.
Yes, sir.
The pole that is going to give you the maximum delay is the dominant pole. So the pole that is going to give you more tau is the dominant pole. When you sketch on a plot, it comes a little, it is close to 0. That is why it is dominant. Dominant does not mean big capacity, big frequency. Dominant means big capacitance, big resistance, big delay, system is slow. Are you getting?
Yes, sir, I got. Sir, and in low frequency, how we find that omega 3 is less than omega 1?
You have to see tau values, no? Take some values. I've given you 1 by GM is 10 ohms.
Yes, sir.
So alpha, our main aim is not omega 3 or omega 1. Our main aim is omega 2. Omega 2 has got the least time constant. That is why it's got the highest frequency.
Okay. Okay, sir. Thank you, sir.
Okay.
So this topic was very difficult. Thank you so much.
Yeah. Yes. Anybody else?
Hello.
Yes.
Sir, 21 if.
Yeah.
Sir, in one of the case you have told that we have to take ID.
Your voice is not clear.
Hello, sir.
Yes.
29. 29 if.
Yeah.
Sir.
Today, sir.
Yes, sir. Today's class.
Where is today's?
So you saved as 14.
Oh. Thank you for that.
Sir, first 21 if, sir.
Yeah.
Sir, why we have taken here ID, sir? I mean, in the circuit you have taken ID current, sir. Why we have taken only ID?
No, you want numerator current and denominator current to be same, no? Already in MOSFET there is only one current, no?
Sir, ID.
No, in MOSFET how many
We
current?
don't have I. Okay. Same current, yes, sir. Yes, sir.
ID equal to
Okay.
IS
And
because
28
zero.
is. Yes, sir. Yes, sir. Yes, sir.
Yeah.
Okay. 28 if.
Yes.
28.
Yeah, tell me.
Sir, here why you are not sir, here why you are not considering right side part, sir?
Because there is no connection between base and collector in the small signal model. Small signal, if you want, we can draw like this.
28, sir.
Yeah, see, small signal is like this, no? Can you see? This base emitter collector. There is no connection between base and collector. That is why. Are you getting?
Okay. Yes, sir. Sir, once open 29.
Huh?
29.
Yeah.
Sir, if we are looking less than we have seen
Your voice is.
I mean, in this problem, we have not taken RL. Hello, sir. In these, not take AC and RLI, sir.
See, the resistance seen through emitter is what? Alpha by GM, no? The resistance seen through emitter is
Yes,
alpha
sir.
by GM.
Yes, sir.
That is why. See those rules, no? You will understand. Resistance
I
seen through
understood.
base R pi,
And
resistance seen through emitter alpha by GM.
30.
Yeah.
గుడ్ ఈవినింగ్ సార్.
Yes.
సార్ ఈ స్టెబిలిటీ ఫ్యాక్టర్ క్యాలిక్యులేషన్ మీద క్వశ్చన్స్ బిట్స్ అండ్ బైట్స్ లో మొత్తం అయ్యే ఉన్నాయి సార్. అవి మనం ఎట్లా సార్ అది?
ఓకే, రేపు ఫస్ట్ రాగానే ఫస్ట్ ఒక ప్రాబ్లం చేస్తా. అవి వేస్ట్ క్వశ్చన్లు అనమాట. అందులో నుంచి ఒక్క బిట్ కూడా రాదు, కానీ మీరు ప్రాక్టీస్ చేసుకోవడం గురించి ఒక ప్రాబ్లం చేస్తారు.
లేదు సార్, అంటే ఆల్రెడీ మేము చాలా స్ట్రగుల్ అవుతున్నాం సార్. ఈ డైలీ 2 సబ్జెక్టులు జరుగుతున్నాయి. అంటే అవసరం లేదనుకుంటే ఏం కదా సార్ అది వదిలేస్తే?
ఏం అసలు ఫస్ట్ ఆఫ్ ఆల్ స్టెబిలిటీ ఫ్యాక్టర్ అనేది దీంట్లో మిల్మెన్ లో ఉండేది. మిల్మెన్ 1960 ముందు ఉన్నవి అవి.
ఓకే ఓకే సార్.
ఇప్పుడు అన్ని మైక్రో ఎలక్ట్రానిక్స్ అయిపోయినాయి కదా. లాస్ట్ 10 నుంచి ఆ క్వశ్చన్లే లేవు.
ఈ బిట్స్ అండ్ బైట్స్ మొత్తం అయ్యే ఉన్నాయి సార్. ఒక 20 క్వశ్చన్లు ఉంటే 10 క్వశ్చన్లు.
ఇప్పుడు ఏఎస్ అకాడమీ 20 ఏళ్ళ ముందు నుంచి ఉంది కదా నాన్న, 25 ఇయర్స్. ఆ పేపర్స్ అన్ని ఇచ్చినారు అనమాట. అంటే మన పేరెంట్స్ రాసేటప్పుడు గేట్ అప్పటి నుంచి ఉన్నాయి అవి.
ఓకే సార్, అదే సార్. అది సార్ ఇంకొకటి మనము ఎప్పుడు చూసినా ఇప్పుడు మనము ఫార్వర్డ్ బియాస్ కాబట్టి 0.7 చేస్తాం సార్. ఇది మన ఏది బిఈ జంక్షన్
డీసీలో 0.7 తీసుకుంటాం.
ఎస్ సార్, కానీ అది మనం సిబి వచ్చేసి మనకి అక్కడ రివర్స్ బియాస్ కాబట్టి అక్కడ 0.7 తీసుకుని. ఇప్పుడు సాచురేషన్ లో కూడా మనకి బిఈ 0.7 ఉంటుందా సార్?
0.2 తీసుకోవాలి. విసి సాట్ 0.2.
విసి కదా సార్ ఈ మనకి బిఈ.
విబి 0.7 వాడేస్తాడు 0.7. డిజిటల్ పేపర్ లో 0.8, అనలాగ్ క్వశ్చన్ లో మోస్ట్లీ 0.7 ఇస్తున్నాడు. అంటే మనము వాడు ఇచ్చిందే తీసుకోవాలా. వాడు 0.7 ఇస్తే 0.7 తీసుకోండి.
ఓకే ఓకే సార్. అంటే సాచురేషన్ ఒకవేళ మెన్షన్ చేయకపోయినా కానీ మనం సాచురేషన్
0.2 ఇస్తాడు.
లేదు సార్, విసి సాట్ కదా సార్. విబి
సాచురేషన్ అని ఏమి ఇవ్వడు. విబిఈ ఆన్ అంటాడు అంతే. అదే తీసుకోవాలా.
ఇంకొకటి సార్, మనం ఇక్కడ బేస్ అండ్ ఎమిటర్ టర్మినల్ ఎందుకు షార్ట్ చేయమంటే డయోడ్ ఆన్ అవ్వాలి కాబట్టి.
అది కలెక్టర్ బేస్ జంక్షన్ ఎలాగో రివర్స్ బయాస్ అయింది. అప్పుడు బీజేపీ యాక్టివ్ రీజన్ లో ఉంటుంది.
నో సార్, నో. అది ఇప్పుడు మనము ఇప్పుడు ఈ ఓన్లీ బేస్ జంక్షన్ కెపాసిటర్ జంక్షన్ ఎందుకు సార్ షార్ట్ చేస్తాం? ఓన్లీ ఇప్పుడు కెపాసిటర్ ఎమిటర్ షార్ట్ చేస్తే ఏమవుతుంది సార్?
ఏది బేస్ ఎమిటర్?
మనం ఇప్పుడు బేస్ ఎమిటర్
షార్ట్ చేస్తే డయోడ్ ఆఫ్ అయిపోతుంది, కట్ ఆఫ్ లోకి వెళ్ళిపోతుంది.
నో సార్, ఇది సార్ ఇప్పుడు మనము బేస్ కలెక్టర్ షార్ట్ చేస్తే మనం దాన్ని డయోడ్ కింద ట్రీట్ చేసి అక్కడ మనం ఈక్వలెంట్ రెసిస్టెన్స్ 1/GM ప్యారలల్ విత్ ఆర్పై.
అవునవును, మీరు బేస్ ఎమిటర్ షార్ట్ చేశారనుకోండి అప్పుడు R0.
నో సార్, ఈ కలెక్టర్ అండ్ బేస్ మనం షార్ట్ చేయము సార్ ఇప్పుడు.
కలెక్టర్ బేస్ షార్ట్ చేస్తే డయోడ్ అది.
నో సార్, ఈ కలెక్టర్ అండ్ ఎమిటర్ మనం ఎప్పుడు షార్ట్ చేయము సార్. అది సార్
లేదు, కలెక్టర్ ఎమిటర్ మీరు షార్ట్ చేస్తే విసి 0 అయిపోతుంది, సాచురేషన్ లోకి వెళ్తుంది.
ఓకే ఓకే, కింద మనం ఆల్రెడీ గ్రౌండ్ ఉంటుంది కాబట్టి ఈ రెండు ఓకే
షార్ట్ అవుతాయి, సాచురేషన్ లోకి వెళ్తుంది డివైస్.
ఓకే సార్, సాచురేషన్ లోకి వెళ్తుంది. ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్.
జంక్షన్ షార్ట్ చేస్తే ఆఫ్ అయిపోతుంది
సార్. ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్ సార్.
Yes.
సార్ వన్ మోర్ సార్.
Yes.
ఈసారి కామన్ ఇప్పుడు మనం కరెంట్ కానీ వోల్టేజ్ కానీ ఓకే సార్. ఈ కరెంట్ కానీ వచ్చేసి ఇప్పుడు మనం కామన్ ఎమిటర్ అయితే ఇట్లా బీటా, ఐసీబై అయితే బీటా అట్లా డైరెక్ట్ ఇచ్చేసి సరిపోతుంది సార్.
అంతే. అసలు కరెంట్ ఉన్నదే ఆడ 3 కరెంట్ రిలేషన్ మనకు ఆల్రెడీ తెలుసు కదా.
ఓకే, నో మ్యాటర్ వాట్ ఏ సర్క్యూట్ అయినా సరే ఇంకా మనకు ఆల్ఫా.
మీకు మరీ వోల్టేజ్ డివైడర్లు ఇచ్చే సర్క్యూట్ లేవు ఇప్పుడు. అన్ని బీజేటీవే ఉన్నాయి కాబట్టి ఉన్నదే ఒక కరెంటు.
కానీ ఇక్కడ మనకి వర్క్ బుక్ లో ఒక క్వశ్చన్ 42 క్వశ్చన్ సార్. అక్కడ కరెంటు 1+ బీటా అవుతుంది కదా సార్. ఎట్లా అంటే మనకి కామన్ ఎమిటర్ కామన్ కలెక్టర్ ఇచ్చాడు సార్ అతను.
ఓకే,
సో కామన్ కలెక్టర్ లో మనకి
కరెంట్ మళ్ళీ డివైడ్ అవుతుందా లోడ్ లోకి, అక్కడ కరెంట్ డివిజన్ అప్లై చేస్తే సరిపోతుంది.
ఓకే సార్, కరెంట్ డివిజన్ అప్లై చేస్తే ఓకే సార్. సో ఓకే, మనం లోడ్ కరెంట్ తీసుకొని ఇన్పుట్ కరెంట్ తీసుకుంటే సరిపోతుంది సార్.
అంతే అంతే.
ఈ ఓకే సార్. ఒకసారి ఇంకొకటి సార్, ఈ ఫిక్స్డ్ బియాస్ మనం ఏం చేసినామంటే డైరెక్ట్ గా విసిసి నుంచి 2 డివైడర్లు వేసి ఒకటి ఇట్లా చేసినాం కదా సార్. ఇంకొకటి రెసిస్టర్ ఏం చేసినంటే సార్, వాడు ఇప్పుడు మన విసిసికి ఇచ్చిండు ఆర్సీ రెసిస్టెన్స్ ఒక రెసిస్టెన్స్ పెట్టాడు మధ్యలో, దాని కింద పాయింట్ పెట్టి దాని బేస్ కి ఫీడ్బ్యాక్ తీసింది సార్. అది ఎలా సార్? అది నెగిటివ్ ఫీడ్బ్యాక్ అని అట్లా ఏమన్నా ఉందా సార్?
నెగిటివ్ ఫీడ్బ్యాక్ దాని డిసి అనాలిసిస్ ఏసీ అనాలిసిస్ రెండు సాల్వ్ చేస్తాను నేను క్లాస్.
ఓకే సార్, అదే సార్, అది కొంచెం ప్రాబ్లం ఉంటే అది మనకి ఇట్లా ఈ ఇంకొకటి సార్, మనము ఇట్లా ఈ వోల్టేజ్ గైన్ కనుక్కున్నప్పుడు మనకి ఇట్లా ఫీడ్బ్యాక్ రెసిస్టెన్స్ అనేది లేదు కదా సార్. అప్పుడు మనం ఎలా సార్ ఒకవేళ వోల్టేజ్ గైన్ కనుక్కోవాలంటే అప్పుడు మనకుంటే?
అదే ఫీడ్బ్యాక్ రెసిస్టర్ లేదు అంటే ఆప్ యాంప్ లో అంటున్నారా, బీజేటీలో?
లేదు సార్, బీజేటీలో సార్. ఇక్కడ డైరెక్ట్ గా మనకి
ఇప్పుడు కామన్ ఎమిటర్ యాంప్లిఫైర్ ఫీడ్బ్యాక్ రెసిస్టర్ లేదుగా, -GMRC కడుతున్నాం కదా.
లేదు సార్, ఒక క్వశ్చన్ ఏం చేసిందంటే సార్, డైరెక్ట్ మనకి ఇట్లా బేస్ నుంచి డైరెక్ట్ గా కలెక్టర్ కి ఒక రెసిస్టెన్స్ ఇచ్చింది సార్, దాన్ని లోడ్ కి కనెక్ట్ చేసింది సార్, ఆర్ఎల్ కి మధ్యలో ఒక రెసిస్టెన్స్ పెట్టేసి. ఈ బేస్ నుంచి ఒక రెసిస్టెన్స్ తో కలెక్టర్ కి ఇచ్చింది సార్. కలెక్టర్ నుంచి అక్కడ నుంచి
ఈ మిల్లర్ ఎఫెక్ట్ అయిపోయిన తర్వాత రేపు ఆ క్వశ్చన్ నేను సాల్వ్ చేయబోతున్నా క్లాస్.
ఓకే సార్, అంటే ఆ క్వశ్చన్ చూసేసరికి అలా అనిపించింది సార్. థ్యాంక్ యూ వెరీ మచ్ సార్. థ్యాంక్ యూ. ఓకే సార్,
నా మైండ్ లో ఉన్నాయి అవన్నీ.
లేదు సార్, అంటే లేదు సార్, అది నేను అట్లా క్వశ్చన్ చూసేసరికి ఏంది చేయలేదు కానీ అట్లా అనిపించింది సార్.
తప్పకుండా చేస్తాను.
థ్యాంక్ యూ వెరీ మచ్.
రైట్. Okay, shall we stop?